The universe is extremely large, and every new finding in astronomy shows that our current knowledge is very limited. From the earliest observations of distant galaxies to the detection of planets orbiting other stars, each discovery has raised more questions than answers. As telescopes improve, scientists continue to identify new problems to study, such as the effects of dark energy, the presence of dark matter that influences the structure of the universe, and unexplained signals that may point to new physical laws. Are there discoveries in the universe that remain unknown and potentially greater than those already made? And if so, what are they? Before we embark on this journey, drop it in the comments below where in the world you're watching from and what time the time is there. Now, settle in as we uncover if there's anything else in the universe so potentially discover. A star is a huge glowing ball made mostly of very hot gas, or plasma, that holds itself together because of its own gravity. The closest star to Earth is the Sun, which is the source of light and heat for our planet. At night, we can see many other stars with the naked eye, although they appear only as tiny points of light because they are so far away. The brightest of these stars have been grouped into patterns called constellations, and smaller patterns called asterisms. Over time, many of the brightest stars were given names. Astronomers have also put together star catalogues, which are like large lists that record the stars we know and give them standardized names and designations. The observable universe is thought to contain somewhere between 10 sextillion, that is a 1 followed by 22 zeros, and 1 septillion, that is 1 followed by 24 zeros, stars. Yet, only about 4,000 stars are visible to the naked eye, and all of them are inside our own galaxy, the Milky Way. The story of a star begins inside a vast cloud of gas and dust in space, known as a nebula. These clouds are mostly made of hydrogen and helium, with small amounts of heavier elements. Under the pull of gravity, parts of the cloud collapse inward, and the material becomes denser and hotter until a star is born. The fate of the star, how long it lives and how it dies, depends mostly on how much mass it has. For most of its life, a star shines because nuclear fusion in its core turns hydrogen into helium. This process releases a huge amount of energy, which travels outward through the layers of the star and eventually radiates into space as light and heat. When a star reaches the end of its life, it can no longer carry out fusion in its core. What happens next depends on its mass. A star may end as a white dwarf, a neutron star, or, if it is massive enough, it can collapse into a black hole. Stars are also responsible for creating most of the chemical elements found in the universe. Inside stars and during the violent deaths of massive stars, supernovae, nuclear reactions form almost all elements heavier than lithium. These enriched materials are blown back into space, mixing with interstellar gas and dust. Later, this material becomes the raw ingredient for new stars and planets, including those like Earth. But before we go deeper into the mysteries of the stars, I want to thank today's sponsor, Mantis Sleep. Working late nights on space documentaries means my schedule is often upside down, and good rest is the one thing that keeps me focused. That's why I use Mantis Sleep. Their sleep masks are designed to block out 100% of light, giving you total blackout sleep whenever and wherever you need it. The material is soft, breathable, and fully adjustable, so it feels comfortable whether I'm taking a short nap in the middle of the day or getting a full night's rest. Mantis Sleep is all about the pro-nap movement, redefining rest as something to be proud of, not guilty about. And honestly, I couldn't agree more. Rest is fuel, and with the right fuel, I can keep exploring stories from the edge of the universe. And here's the best part. You can try it for yourself today. Just visit mantisleep.com and use my code Spacedust at checkout for 10% off your order. So whether you want a quick recharge during the day or deep uninterrupted rest through the night, check out Mantis Sleep by clicking the link in the description below. By studying the brightness of stars, their light spectrum, and how they move in the sky over time, astronomers can learn about their mass, age, chemical makeup, distance, and motion through space. Stars are not always alone. They can form systems with other objects like planets, or with other stars. Two stars orbiting one another are called binary star systems, and their strong pull on each other can change how both of them evolve. Many stars also belong to even larger groups, such as star clusters or galaxies. Throughout history, stars have played an important role in human life and culture. They were central to religion, mythology, and rituals. People used them for navigation, to keep track of seasons, and to create calendars. Early astronomers noticed that some objects in the sky seemed fixed in place, while others, which they called wandering stars, what we now know as planets, changed position over days or weeks. Many ancient people believed the stars were fixed on a great celestial sphere that never changed. To make sense of the night sky, astronomers grouped stars into constellations and used them to follow the motion of the sun and planets. The yearly movement of the sun against the background of stars was used to build calendars that guided farming and other activities. The Gregorian calendar, which is widely used today, is based on the motion of Earth around the sun. The oldest known star chart dates back to ancient Egypt in the year 1534 before Christ. Ancient Babylonian astronomers created the earliest known star catalogues during the second millennium before Christ, especially in the Kassite period, between about 1531 and 1155 before Christ. In Greece, Aristillus, with the help of Timocharis, made one of the first star catalogues around the year 300 before Christ. In the 2nd century before Christ, Hipparchus created a catalogue of 1020 stars which was later used by Ptolemy. Hipparchus also recorded the first nova, or new star. Many of today's star names and constellations come from Greek astronomy. Chinese astronomers, however, realized that the heavens were not unchanging. They recorded the appearance of new stars, including the first documented supernova in the year 185 after Christ. The brightest supernova ever recorded, known as SN 1006, appeared in the year 1006. It was observed by the Egyptian astronomer Ali ibn Ridwan, as well as Chinese astronomers. Another major supernova, SN 1054, created what is now known as the Crab Nebula, and was observed by both Chinese and Islamic scholars. In the Middle Ages, Islamic astronomers gave Arabic names to many stars that are still used today. They built the first large observatories and created detailed star catalogues. In the year 964, the Persian astronomer Abd al-Rahman al-Sufi wrote the Book of Fixed Stars, describing clusters and even galaxies like Andromeda. In the 11th century, Abu Rayhan Biruni studied the Milky Way and suggested it was made of countless small stars. Around the year 1106, the Andalusian astronomer Ibn Bajjah proposed that the Milky Way appeared as a continuous band because of refraction of light. In Europe, Tycho Brahe in the 16th century found new stars in the sky, showing the heavens could change. In 1584, Giordano Bruno suggested that stars were like the Sun and might have planets orbiting them, possibly even Earth-like ones, an idea earlier suggested by Greek thinkers and later supported by Islamic scholars. By the 17th century, most astronomers agreed that stars were suns at great distances. Isaac Newton, to explain why the star's gravity did not collapse the universe, suggested they were spread evenly in all directions. In 1667, Geminiano Montanari noticed changes in the brightness of the star Algol. Later, Edmund Halley showed that some stars had moved since ancient times, proving they were not fixed. William Herschel, in the 1780s, tried to map the distribution of stars. He observed 600 directions in the sky and counted stars along each one, showing that more stars appeared toward the Milky Way's centre. His son, John Herschel, later did the same in the southern hemisphere. William Herschel also discovered that some stars are not just lined up by chance, but actually orbit each other, forming binary systems. The study of stars through their light, a branch of science called stellar spectroscopy, began in the early 19th century with the careful work of Joseph von Fraunhofer and Angelo Secchi. These two pioneers noticed something remarkable when they compared the light from different stars such as Sirius to the light from our Sun. They saw that the dark lines, known as absorption lines, in the spectrum of each star were not the same. These lines appear because the atmosphere of a star absorbs certain frequencies of light. By examining the strength and number of these lines, Fraunhofer and Secchi realized that stars are not all alike. In the year 1865, Secchi began to group stars into categories based on their spectra, creating the very first system of stellar classification. This system was later refined and transformed into the modern version we still use today by Annie Jump Cannon during the early years of the 20th century. In the year 1838, Friedrich Bessel achieved something extraordinary. He was the first person to directly measure the distance to a star. That star was 61 Cygni, and Bessel found it to be about 11.4 light-years away from Earth. He used a method called parallax, which relies on the apparent shift of a star's position when viewed from different points in Earth's orbit. This discovery proved just how unimaginably far apart stars are in space. Around the same period, astronomers also began to study pairs of stars known as double stars with greater attention. In the year 1834, Bessel noticed that Sirius, the brightest star in the night sky, was moving in a slightly unusual way. He concluded that this motion was caused by a hidden companion star, one we could not yet see directly. Later, in the year 1899, Edward Pickering made another breakthrough when he discovered the first spectroscopic binary star. He observed that the light from the star Mizar showed spectral lines that regularly split apart and came back together over a period of 104 days. This revealed the presence of two stars orbiting each other so closely that they could not be separated by a telescope. Other astronomers, such as Friedrich Georg Wilhelm von Struve and Sherburne Wesley Burnham, devoted years to carefully observing binary star systems. Their detailed records made it possible to calculate the masses of stars by working out the mathematics of their orbits. In fact, as early as the year 1827, Felix Savary had already solved the problem of how to derive the orbit of binary stars directly from telescope observations. His work opened the door to the precise study of stellar masses and movements. The 20th century brought faster and more powerful progress in the science of stars. Photography quickly became one of the most important tools for astronomers. Carl Schwarzschild showed that the colour of a star could reveal its temperature. He did this by comparing how bright a star looked to the eye, known as its visual magnitude, with how bright it appeared on photographic plates, known as photographic magnitude. Soon after, the invention of the photoelectric photometer allowed astronomers to measure the brightness of stars at different wavelengths of light with great accuracy. Then, in the year 1921, Albert Abraham Michelson made history by directly measuring the diameter of a star for the first time. Using an interferometer attached to the giant Hooker telescope at the Mount Wilson Observatory, he was able to calculate the size of a distant star with surprising precision. During the early decades of the 20th century, some of the most important theoretical work in astrophysics also took place. In the year 1913, the Hertzsprung-Russell diagram was introduced, providing a powerful way to understand the relationships between a star's brightness, colour, and stage of life. This diagram became a central tool in the study of stellar evolution. Not long after, detailed models of how stars live, burn their fuel, and change over time began to emerge. In the year 1925, Cecilia Payne-Gaposchkin made a bold and revolutionary claim in her doctoral thesis. She proposed that stars are made mostly of hydrogen and helium, not of heavier elements as many scientists had previously assumed. Later, with the rise of quantum physics, astronomers could explain stellar spectra in even greater detail and determine the exact chemical composition of stellar atmospheres. Most of the stars we know in detail have been observed within our own cosmic neighbourhood, called the local group of galaxies. The majority of these stars lie in the visible part of the Milky Way, the galaxy we live in, along with its smaller satellite galaxies. Astronomers have built detailed star catalogues that chart the positions and properties of stars across our galaxy. Beyond the Milky Way, astronomers have managed to observe certain kinds of variable stars, such as Cepheid variables, in other galaxies. For instance, such stars have been seen in the M87 and M100 galaxies, both of which belong to the Virgo cluster. Astronomers have also detected very bright individual stars in a handful of other nearby galaxies. Even more astonishing discoveries have come through the use of gravitational lensing, a phenomenon predicted by Einstein's theory of relativity. In rare cases, the light from a single distant star is magnified by the gravity of an intervening galaxy, acting like a natural cosmic telescope. Using this effect, astronomers observed a single star nicknamed Icarus, located an almost unbelievable 9 billion light-years away. This observation pushed the limits of how far into the universe we can study individual stars, showing that even across billions of years of cosmic history, starlight can still reach us. The idea of constellations goes back thousands of years, long before modern science. During the time of the Babylonians, people who carefully watched the night sky noticed that certain stars seemed to form patterns when connected in the mind's eye. These shapes were often linked to natural forces or woven into the myths and legends of their cultures. Out of all the different star groupings, 12 constellations were found to lie along the path the Sun appeared to travel across the sky each year. This path is called the ecliptic, this path is called the ecliptic, and those 12 constellations later became the foundation of what we now know as astrology. Over time, many of the brightest individual stars were also given names. These names often came from Arabic or Latin, since those cultures had a strong influence on astronomy during the Middle Ages. But naming stars was not just about identification, it was also about storytelling. For both constellations and individual stars, people created myths and tales to explain their presence. To the ancient Greeks, not all bright points in the sky were considered stars. They noticed that a few of them seemed to wander against the backdrop of the fixed stars. The Greeks called these wandering objects planets, which means wanderers. They associated them with powerful gods. For example, the planet Mercury was linked to Hermes, the swift messenger god. Venus was connected to Aphrodite, goddess of love and beauty. Mars was seen as Ares, the god of war. Jupiter was named after Zeus, the king of the gods, and Saturn was tied to Cronus, the ancient ruler of time. The outer planets Uranus and Neptune were also named after gods, but they were not discovered until much later, because their faint light made them invisible to the naked eye in ancient times. By around the year 1600, astronomers began using constellation names as a way to label stars found in those parts of the sky. A German astronomer named Johann Bayer created detailed star maps and introduced a clever system of labeling stars with Greek letters within each constellation. Later, the English astronomer John Flamsteed developed another system. He organised stars by their position in the sky according to right ascension, the celestial version of longitude, and published this in his famous work Historia Caelestis Britannica in the year 1712. This system of numbering is still known today as the Flamsteed designation. In modern times, the official authority in charge of naming stars and other celestial bodies is the International Astronomical Union, often called the IAU. Within this organisation, a special group known as the Working Group on Star Names catalogues and approves proper star names. Even though private companies sometimes try to sell official star names to the public, these names are not recognised by professional astronomers or by the IAU. The British Library has described such businesses as unregulated and misleading, and the Department of Consumer and Worker Protection in New York City even issued a violation against one company for engaging in deceptive trade practices. When astronomers describe stars, they often compare them to the Sun. Instead of using large and complex units, they express a star's mass, brightness, or size in solar units, meaning how many times larger or smaller it is compared to the Sun. In the year 2015, the International Astronomical Union established a set of fixed solar values that astronomers can use as standard measures. For example, the Sun's mass was defined to be about 1.9885 times 10 to the power of 30 kilograms. Even though future measurements may refine details, these standard values remain fixed for ease of comparison. For measuring vast distances, astronomers often use another convenient unit called the astronomical unit, or AU. This represents the average distance between the Earth and the Sun, which is about 150 million kilometers, or around 93 million miles. In the year 2012, the IU made the astronomical unit an exact value: 149,597,870,700 meters. Stars themselves are born in giant clouds of gas and dust, called molecular clouds. These clouds are not dense compared to everyday matter. In fact, they are thinner than the inside of a laboratory vacuum chamber, but they are still denser than their surroundings in space. Most of their material is hydrogen, with roughly 1/4 helium and a small fraction of heavier elements. A well-known example of such a star-forming region is the Orion Nebula. Stars usually form in groups, ranging from a few dozen to many hundreds of thousands. The most massive stars in these groups shine so intensely that they light up the surrounding gas, ionize hydrogen, and create glowing regions called H2 regions. This radiation can eventually disrupt the cloud itself, halting further star formation. Every star spends most of its life in what astronomers call the main sequence. In this stage, a star steadily burns hydrogen into helium in its core through nuclear fusion. Yet not all stars are the same. Their life cycles differ greatly depending on their mass. Very low-mass stars, weighing less than half the mass of the Sun, circulate their material evenly throughout their interiors. This means they never develop separate layers for nuclear burning, and they never expand into red giants. Instead, when they run out of hydrogen fuel, they become white dwarfs made mostly of helium. Since their lifetimes are longer than the age of the universe itself, none of these stars has yet completed this journey. Low-mass stars like the Sun weigh between about half and a little more than twice the Sun's mass. When their core hydrogen runs out, they swell into red giants and begin to burn helium. Eventually, they shed their outer layers, forming beautiful planetary nebulae, while their dense cores remain behind as white dwarfs made of carbon and oxygen. Intermediate mass stars, between a little more than twice and up to about 8 times the Sun's mass, go through a similar path but without dramatic helium flashes. They spend a long time in what astronomers call the red clump phase, before eventually becoming white dwarfs. Massive stars with more than about 8 times the Sun's mass live fast and die young. They burn through their hydrogen quickly, expand into enormous supergiants, and fuse heavier and heavier elements in their cores. At the end of their lives, their cores collapse, and they explode as supernovae, scattering newly formed elements into space. The birth of a star begins deep inside a giant molecular cloud, huge, cold regions of space filled with gas and dust. Inside these clouds, gravity starts to disturb the balance when certain areas become denser than their surroundings. This instability, called gravitational instability, can be set off by several events: the pressure of powerful radiation from nearby massive stars, the shock waves of expanding gas bubbles in space, the collision of 2 different molecular clouds, or even the collision of entire galaxies, which can lead to what astronomers call a starburst galaxy, where new stars are formed in great numbers. When a region inside the cloud reaches a high enough density to meet what scientists call the gene's instability, gravity takes over. The region collapses inward under its own pull. As this collapse continues, smaller dense pockets of gas and dust form, known as Bok globules. Inside these globules, gravity squeezes the material tighter and tighter, and as it does, the gravitational energy changes into heat. The temperature steadily rises. At the heart of the globule, when the balance between gravity pulling inwards and pressure pushing outwards stabilizes, a new object forms. This object is called a protostar, a kind of star in the making. These protostars are usually surrounded by a protoplanetary disk, a spinning ring of dust and gas from which planets, moons, and other objects can later form. At this stage, the protostar shines mainly because of the energy from gravity pulling material inward, not yet from nuclear fusion. This early stage of contraction and heating can last around 10 million years for a star the size of our Sun, and as long as 100 million years for a small red dwarf star. Stars that are still young but less massive than about 2 times the Sun's mass are called T-Tauri stars, while those larger than this are called Herbig AB stars. These new stars often release dramatic jets of gas along their axis of rotation. These jets can help the forming star by reducing its spin, and sometimes they create glowing patches of light in space called Herbig halo objects. The jets, combined with the radiation from larger nearby stars, also help blow away the leftover gas and dust that once surrounded the forming star. During their early lives, T-Tauri stars follow what astronomers call the Hayashi track. Along this path, the star continues to shrink in size and becomes dimmer while keeping nearly the same surface temperature. Smaller T-Tauri stars follow this path until they settle into the main sequence, the long, stable stage of a star's life. More massive young stars, however, shift onto the Henye track as they evolve. Interestingly, most stars are not alone. They are found in pairs called binary star systems. The way these binaries form depends on the conditions inside the original cloud. For a star to form, the gas cloud must lose some of its spin or angular momentum. Often, this is achieved by the cloud splitting into 2 or more stars, which share out that spin among themselves. In young clusters of stars, gravitational encounters can change binary systems further. Weakly bound pairs tend to break apart, while tightly bound pairs grow even closer together. Over time, this process creates the 2 main groups of binary star systems that astronomers observe today. Once a star fully forms, it spends about 90% of its life quietly fusing hydrogen into helium at its core through nuclear reactions that require extremely high temperatures and pressures. At this stage, the star is said to be on the main sequence and is usually called a dwarf star. From the very beginning of this stage, called the zero-age main sequence, helium slowly builds up in the core, the fusion rate gradually increases, and both the star's temperature and brightness rise. For example, our Sun has already become about 40% brighter since it entered the main sequence about 4,600,000,000 years ago. All stars also produce a steady outflow of charged particles known as stellar wind. For most stars, this loss of material is tiny and does not affect their evolution much. The Sun, for instance, loses only a tiny fraction, about 1/10,000th of 1%, of its mass over its entire lifetime. But very massive stars lose much more. They can shed between 1/10,000,000th and 100,000th of their solar mass every year, and stars that start with more than 50 times the Sun's mass may lose more than half of it before leaving the main sequence. The length of time a star stays on the main sequence depends mostly on its mass and how quickly it burns its fuel. The Sun, for example, is expected to live for about 10 billion years. Massive stars, on the other hand, consume their fuel at a furious pace and live only for a few million years. Very small stars, such as red dwarfs that weigh less than about 1/4 of the Sun's mass, burn their fuel very slowly and can last for incredibly long periods. A red dwarf can live for about 1 trillion years, and the smallest ones, with only about 8% of the Sun's mass, may survive for around 12 trillion years. As they age, red dwarfs grow hotter and brighter, but once they run out of hydrogen, they shrink into white dwarfs and slowly cool down. Because the lifetime of these stars is so enormous, far greater than the current age of the universe, about 13,800,000,000 years, no red dwarf has yet lived long enough to leave the main sequence. While mass is the most important factor in a star's evolution, another factor also plays a big role: the amount of elements heavier than helium that the star contains. Astronomers call all these heavier elements metals, and the proportion of them in a star is called its metallicity. A star's metallicity can affect how long it takes to burn through its fuel, how its magnetic fields form, and how strong its stellar wind is. Old stars, known as population 2 stars, have much lower metallicity than younger population 1 stars. This difference comes from history. When the universe was young, the first stars contained almost no heavy elements, but as stars aged and died, they released these elements into space, enriching the molecular clouds. Each new generation of stars therefore formed with more and more heavy elements mixed in. As a star that has at least a little less than 1/2 the mass of our Sun reaches the end of its hydrogen supply at its core, an important change begins. Instead of fusing hydrogen at its center, the star starts burning hydrogen in a shell that surrounds a core of helium. This change has a dramatic effect. The outer layers of the star expand and become much cooler, and the star swells into what astronomers call a red giant. In some cases, the star's core or the shells around it begin to fuse heavier elements, not just hydrogen. As the star grows larger, it throws away part of its mass into space. This lost material, enriched with newly created elements, drifts into the galaxy and will eventually become the raw material for future generations of stars. Our own Sun will face this fate in about 5 billion years. At that time, it will enter the stage where helium starts to burn in its core. The Sun will expand to nearly 1 astronomical unit in radius, which is about 150 million kilometers, a size more than 250 times greater than it is today. During this phase, it will lose around 30% of its mass. As the hydrogen-burning shell continues to pile more helium into the core becomes hotter and more massive. In stars with up to a little more than 2 times the mass of the Sun, the helium core becomes degenerate, meaning the atoms are packed so tightly that they no longer behave like normal matter. When the temperature rises high enough, helium fusion suddenly begins in an explosive event called a helium flash. This forces the star to shrink quickly, while its surface grows hotter. The star then settles into a new stable stage of life on the so-called horizontal branch of the Hertzsprung-Russell diagram. In more massive stars, helium fusion begins more smoothly, before the core becomes degenerate. Such stars may pass through a stage known as the red clump, where they slowly burn helium, before their structure changes and they move to the horizontal branch. After a star has finished burning the helium in its core, fusion continues in a shell around a core now made mostly of carbon. The star enters what astronomers call the asymptotic giant branch, or AGB. This stage looks similar to the red giant phase, but the star shines even more brightly. The most massive of these stars may briefly ignite carbon fusion before their cores become degenerate. During the AGB phase, stars are unstable. They undergo thermal pulses in which their brightness changes and large amounts of matter are thrown into space. Over time, they can lose between 50 and 70% of their total mass. Because these stars mix their inner layers through strong convection, the material they eject is rich in the products of fusion, such as carbon and oxygen. Because these stars mix their inner layers through strong convection, the material they eject is rich in the products of fusion, such as carbon and oxygen. This expelled matter creates a glowing shell of gas called a planetary nebula. Eventually the nebula fades and spreads out, enriching the interstellar medium. In this way, future stars, planets, and even life itself are made of the star stuff left behind by earlier stars. Stars that begin with more than about 9 times the mass of the Sun evolve differently. During their helium-burning stage, they expand first into blue supergiants and later into red supergiants. The most massive stars, those above about 40 solar masses, such as Alnilam, the bright blue star at the centre of Orion's belt, never become red supergiants. Instead, because they lose mass at an incredible rate, they transform into what are called Wolf-Rayet stars. These stars show unusual spectra filled with emission lines from heavy elements that have been brought up to the surface through intense convection and the stripping away of their outer layers. When helium is finally used up in the core of a massive star, the core contracts again. The temperature and pressure rise high enough for the fusion of heavier elements to begin. First carbon fuses, then neon, then oxygen, and then silicon. In the last stages of a massive star's life, fusion takes place in a series of shells arranged like the layers of an onion. The outermost shell burns hydrogen, the next one burns helium, deeper shells burn carbon, neon, oxygen, and so on. The process ends once the core is filled with iron. Iron nuclei are so stable that fusing them does not release energy. This means the star can no longer generate the energy it needs to resist collapse. Some massive stars are unstable even before this final collapse. A special group known as luminous blue variables can erupt violently, shedding huge amounts of their mass into space. These events, which make the star appear dramatically brighter for a time, are sometimes called supernova imposters because they look like supernova but do not destroy the star. A famous example is Eta Carinae, which experienced a massive outburst known as the Great Eruption in the 19th century. As a star nears the end of its life, dramatic changes begin deep within its core. The inner core starts to shrink under the pull of gravity, and this shrinking raises the intensity of radiation pouring out from it. The powerful radiation creates so much outward pressure that it pushes the star's outer gas layers away. These drifting shells of gas spread out into space, glowing beautifully as what astronomers call a planetary nebula. What remains after the atmosphere is cast off depends on how heavy the star's leftover core is. If the core weighs less than about 1.4 times the mass of our Sun, it collapses further until it becomes a small, extremely dense object about the size of our Earth, known as a white dwarf. A white dwarf is so dense that its matter is in a strange state called electron-degenerate matter. It no longer behaves like ordinary plasma, and no further collapse can take place because its mass is too small. White dwarfs gradually cool over time, fading dimmer and dimmer, and after an unimaginably long stretch of time, they may become invisible remnants called black dwarfs. For massive stars, the story ends far more violently. In these giants, nuclear fusion continues until the core builds up iron. Once the iron core grows heavier than about 1.4 solar masses, it can no longer support itself. At that moment, the core suddenly collapses. Electrons are crushed into protons, creating neutrons, neutrinos, and bursts of powerful gamma rays. The collapse triggers a massive shockwave that rips through the star's outer layers, blowing it apart in a titanic explosion known as a supernova. A supernova shines so brightly that for a short while, it can outshine the star's entire galaxy. In our own Milky Way, such explosions have been seen throughout history as brilliant new stars appearing suddenly in the sky, even visible to the naked eye. After the explosion, the outer layers are blasted away into space, sometimes leaving behind glowing clouds like the Crab Nebula. The collapsed core, however, survives in a new and exotic form. If the core is not too massive, it becomes a neutron star, a city-sized sphere made almost entirely of neutrons, where matter is packed more densely than anywhere else known. Some neutron stars reveal themselves as pulsars, flashing beams of radiation across space, or as powerful X-ray sources. But if the collapsed core is extremely heavy, more than about 4 times the Sun's mass, nothing can stop gravity. The star becomes a black hole, an object so dense that even light cannot escape. The violent death of stars is not wasted, however. The outer layers thrown off during these explosions contain heavy elements such as carbon, oxygen, iron, and others. These elements are scattered into space, mixing with interstellar gas. Over time, they are recycled into new stars and planets. Without this process, rocky worlds like Earth could not exist. The winds of massive stars and the outbursts of supernovae also play a vital role in shaping the vast clouds of gas and dust that make up the interstellar medium. The life cycle of stars can take even more fascinating turns in binary systems. Unlike single stars, binary stars often share material when one of them grows into a red giant. If the stars are close enough, the swollen outer layers of one can spill over into the gravitational pull of the other. This mass transfer leads to many unusual phenomena: contact binaries, common envelope binaries, cataclysmic variables, blue stragglers, and even type Ia supernovae. In some cases, this exchange of matter leads to the puzzling algal paradox, where the star that appears younger is actually the one that has lost much of its mass. Because so many stars exist in pairs or in even larger systems, astronomers study binary star evolution very closely. Roughly half of all Sun-like stars are in binaries, and for stars more massive than the Sun, the percentage is even higher. This changes how certain stars form, how some explode, and how heavy elements are distributed into space. Some researchers even argue that binary systems hold the key to explaining the origins of massive evolved stars like luminous blue variables, Wolf-Rayet stars, and the progenitors of certain kinds of supernovae. In many cases, single stars cannot lose their outer layers quickly enough on their own, but mass transfer in binaries may solve this puzzle. Stars are rarely found floating alone in the universe. Instead, they gather together into galaxies made up of stars, gas, and dust. A large galaxy such as the Milky Way contains hundreds of billions of stars. Across the universe, astronomers estimate there are more than 2 trillion galaxies. Most galaxies are smaller than the Milky Way, but even so, the total number of stars in the cosmos is staggering, between 10 sextillion and 1 septillion, that is, a 1 followed by 22 to 24 zeros. This is more stars than there are grains of sand on all the beaches of Earth. Stars are most often found within galaxies, but in giant galaxy clusters, as much as 10 to 50% of the light may come from stars drifting between galaxies, no longer bound to any single one. Multi-star systems also exist in great numbers. The simplest of these are binary stars, 2 stars orbiting each other. But systems of 3, 4, or more stars are known as well. For the sake of stability, many of these complex systems are organized into hierarchical sets, where pairs of stars orbit each other and those pairs orbit other stars. Even larger gatherings are known as star clusters. These range from small groups with only a few stars to open clusters containing dozens, hundreds, or thousands, and all the way up to huge globular clusters with hundreds of thousands of stars. All of the stars in a cluster formed from the same giant cloud of gas, which is why they are usually of similar age and chemical makeup. Interestingly, many or perhaps even most stars may have been born in multiple star systems. This is especially true for massive O and B-type stars, where about 80% are part of multiple systems. For smaller stars, the percentage drops. Only about 1/4 of red dwarfs have companions. But since about 85% of all stars in the Milky Way are red dwarfs, it means that the majority of stars in our galaxy are probably solitary red dwarfs. A study carried out in the year 2017 on the Perseus molecular cloud showed that most newly formed stars were born in pairs. The data even suggested that perhaps all stars began life as binaries, though some later split apart, leaving behind the single stars we see today. The closest star to Earth, apart from our own Sun, is Proxima Centauri, which lies at a distance of about 4.2465 light-years away. To put that in more familiar terms, this equals about 40.175 trillion kilometers. If a spacecraft were to travel at the same speed as the space shuttle once orbited Earth, around 8 kilometers every second, or about 29,000 kilometers per hour, the journey to Proxima Centauri would take roughly 150,000 years. Distances of this scale are fairly typical between stars in the flat, disc-shaped regions of galaxies. However, In the crowded centres of galaxies or inside tight groups of stars known as globular clusters, stars can be packed much closer together. On the other hand, in the faint outer halos that surround galaxies, stars may be separated by much larger distances. Because stars are usually so far apart, especially outside the central regions of galaxies, actual collisions between them are extremely rare. In denser areas, such as the very heart of globular clusters or the centres of galaxies, such collisions are more likely. When two stars do collide or interact, they can create unusual objects called blue stragglers. These stars shine hotter and bluer than the rest of the stars around them in the cluster. According to normal rules of stellar evolution, such stars should already have grown old and dimmed, but collisions or mergers make them appear much younger than they actually are. The initial mass of a star, the amount of matter it was born with, determines almost everything about it. This includes how bright it will shine, how large it will become, how it will evolve, how long it will live, and even how it will eventually die. Most stars that we see are between 1 billion and 10 billion years old, though some may be nearly as ancient as the universe itself, which is about 13.8 billion years old. The oldest known star so far is HD 140283, often called the Methuselah star, with an estimated age of about 14.5 billion years, give or take nearly 1 billion years. Even though this number seems older than the universe itself, the measurement uncertainty means it does not actually conflict with the universe's true age, which was precisely calculated by the Planck Space Telescope. The heavier a star is, the shorter its life. This is because greater mass means greater pressure inside the core, which makes nuclear fuel burn much faster. Very massive stars may only live for a few million years before burning out, while the smallest stars, known as red dwarfs, use their fuel extremely slowly. These tiny stars can shine for tens of billions or even hundreds of billions of years, far longer than the current age of the universe. When new stars form today in our Milky Way galaxy, their material is made of about 71% hydrogen, about 27% helium, and only a small fraction of heavier elements. Astronomers usually measure this heaviness by looking at the amount of iron in the star's outer layers, because iron is common and easy to detect in a star's spectrum. Interestingly, the amount of heavy elements in a star often gives clues about whether it is likely to have planets. Some stars are extremely poor in heavy elements. As of the year 2005, the record holder was a faint star named He 1327-2326, which has only about 1/200,000th of the Sun's iron content. At the opposite extreme, the star Mu Leonis contains almost twice as much iron as the Sun, while another star, 14 Hercules, which is known to have planets, contains nearly 3 times as much iron. Certain stars are also known as chemically peculiar stars because they have strange amounts of elements like chromium or rare earth metals. Cooler stars, including our Sun, often have conditions that allow molecules, made of 2 or more atoms, to form in their outer layers. Because stars are so distant, every star other than the Sun appears to our eyes as a tiny point of light in the night sky. Their apparent twinkling is caused by the constant motion of Earth's atmosphere. Only the Sun, being so near, looks like a glowing disk and provides daylight. Apart from the Sun, the star that looks largest from Earth is R Doradus, which still has an apparent size of only about 0.057 arcseconds, far too small for the naked eye to notice. Most stars are so small in apparent size that normal ground-based telescopes cannot resolve their surfaces. To study them, astronomers use special techniques like interferometry, which combines the light from multiple telescopes, or occultation, where the exact moment a star disappears behind the Moon, or reappears again, is used to measure its diameter. Stars themselves vary enormously in actual size. On the smallest end are neutron stars, the compact remnants of dead stars, which measure only about 20 to 40 kilometers across. On the opposite extreme are supergiant stars such as Betelgeuse in the constellation Orion, which has a diameter about 640 times greater than that of the Sun, but with a much lower density. The way a star moves through space relative to the Sun reveals much about its origin, its age, and even the structure of the galaxy itself. Astronomers describe this movement in 2 parts: the radial velocity, which measures how fast a star is moving toward or away from us, and the proper motion, which describes how it drifts sideways across the sky. Radial velocity is measured using the Doppler shift of light, while proper motion is measured extremely precisely in milliarc seconds per year. By combining proper motion, distance, and radial velocity, astronomers can calculate the star's true speed through space. Nearby stars often show the fastest proper motions, making them excellent candidates for detailed measurements. Younger stars, called population 1 stars, usually move more slowly and in more circular paths around the galaxy. Older stars, called population 2 stars, tend to move faster and follow more elliptical or tilted orbits. By studying these motions, astronomers can sometimes trace many stars back to the same birthplace, a giant cloud of gas and dust. Groups of stars that share a common origin in this way are called stellar associations. The magnetic field of a star is not something that exists on its surface alone. It is born deep inside the star. In certain inner regions, hot gases and plasma move around in swirling currents. This motion, called convection, acts very much like the spinning coils inside a dynamo, the kind of machine once used to generate electricity. In both cases, moving electrical charges create powerful magnetic fields. These invisible fields stretch far and wide, reaching across the entire star and even extending far beyond its outer atmosphere. The strength of a star's magnetic field is not the same for every star. It depends on how massive the star is, what it is made of, and especially how fast it spins. The more quickly a star rotates, the more active its magnetic surface tends to be. This activity reveals itself in several ways. One striking feature is the appearance of star spots, dark, cooler regions on the star's surface where magnetic forces are strongest. Another dramatic display comes from coronal loops. These are glowing arcs of plasma that follow curved magnetic field lines, stretching from the star's surface high into its outer atmosphere, the corona. Alongside these phenomena, stars can also unleash sudden, violent stellar flares, bursts of high-energy particles thrown out into space, all caused by tangled magnetic forces snapping and reconnecting. Young stars are especially restless. Because they rotate very quickly, their magnetic fields are strong and unstable, producing constant surface storms. Over time, however, their own magnetic fields act like a brake, tugging against the star's stellar wind and gradually slowing its spin. As a result, older stars, such as our own Sun, rotate much more slowly and show calmer levels of activity. But even the Sun is not always steady. Its activity rises and falls in cycles, sometimes becoming almost completely quiet. A famous example of this silence is the Maunder minimum, a period lasting about 70 years, from the middle of the 17th century to the early 18th century, when the Sun produced almost no sunspots at all. Stars themselves come in an extraordinary range of sizes. Some are less than half as massive as the Sun, while the largest can exceed 200 times the Sun's mass. One of the giants is Eta Carinae, a monstrous star with somewhere between 100 and 150 times the mass of the Sun. Yet stars this massive live fast and die young, burning through their fuel in only a few million years. Studies suggest that in the current age of the universe, there is an upper limit to how big a star can be, about 150 solar masses. Beyond this point, the intense radiation pressure pushes away the gas that would otherwise allow the star to grow larger. However, in the R136 cluster within the Large Magellanic Cloud, some stars appear even bigger. Astronomers believe these record-breaking giants may have formed when two massive stars collided and merged, bypassing the natural limit. The very first stars that lit up the universe after the Big Bang may have been even more massive. Because these early stars contained no heavy elements, only hydrogen, helium, and a trace of lithium, they could grow to colossal sizes, possibly as large as 300 times the mass of the Sun. These so-called population 3 stars burned brightly in the young cosmos, creating the very first heavy elements, the building blocks needed for planets and life. In June of the year 2015, astronomers announced possible evidence of such ancient stars in a distant galaxy known as Cosmos Redshift 7, lying at a redshift of 6.60, meaning we are seeing it as it was when the universe was still very young. At the opposite extreme of the size scale lies the smallest known star capable of sustaining nuclear fusion at its core. 2 mass, J05231403. It has only about 80 times the mass of Jupiter, making it tiny by stellar standards. For stars with a composition similar to the Sun's, the theoretical minimum mass needed to start fusion is around 75 times the mass of Jupiter. If a star has very low metallicity, meaning very few elements heavier than helium, then the smallest possible star can be a bit larger, about 8% of the Sun's mass, or roughly 87 times the mass of Jupiter. Below this boundary lie the mysterious brown dwarfs, objects that are too massive to be called planets, but not quite massive enough to be true stars. The size and mass of a star also determine the pull of its surface gravity. Enormous giant stars spread out over a huge volume have very weak surface gravity compared to compact main sequence stars. On the other hand, compact stellar remnants like white dwarfs or neutron stars have crushingly strong surface gravity. This gravity even leaves fingerprints in the star's spectrum. The stronger the gravity, the broader the absorption lines appear. A star's rate of rotation can be measured in two main ways, either through the patterns revealed in its spectrum or by directly tracking the movement of its star spots. Young stars often spin at incredible speeds, sometimes faster than 100 km per second at the equator. One dramatic example is the hot blue star Achernar, which rotates at about 225 km per second. This speed makes its equator bulge outwards so much that the star's equatorial diameter is more than 50% greater than the distance across its poles. It rotates just shy of the critical speed of about 300 km per second, at which point the star would tear itself apart. In contrast, our Sun is far more leisurely. Depending on latitude, it rotates once every 25 to 35 days, with an equatorial speed of less than 2 km per second. As stars age, their magnetic fields and stellar winds gradually slow down their spin. But not all stars follow this gentle pattern. Degenerate stars, those that have collapsed into compact remnants, spin differently. While their smaller size should make them spin extremely fast due to conservation of angular momentum, much of their spin has already been lost through powerful stellar winds during their earlier life. Still, some remnants, such as pulsars, can rotate at breathtaking speeds. The pulsar at the centre of the Crab Nebula, for instance, spins about 30 times every single second. Over time, even this incredible rotation gradually slows as the pulsar radiates energy into space. The surface temperature of a star that is still on the main sequence, that is, in the long middle stage of its life, is determined mainly by two things: the amount of energy being produced deep in its core and the overall size or radius of the star. Astronomers often estimate this temperature by studying something called the colour index of the star, which is essentially a measure of how its light looks when seen through different colour filters. The temperature usually given for a star is called its effective temperature. This is not the exact real temperature of its surface, but rather the temperature that an ideal black body would have if it radiated the same amount of energy per unit area. In reality, the surface is only part of the story, because the temperature rises dramatically as you go inward. In the cores of stars, the temperature can soar to many millions of degrees on the Kelvin scale. The temperature of a star directly influences which atoms inside it are stripped of their electrons, a process called ionization. This, in turn, leaves a pattern of dark absorption lines in the star's spectrum, which astronomers can study to learn about the star's properties. The surface temperature, together with the star's true brightness, called its absolute magnitude, and its spectral absorption features, is one of the key tools used to classify stars. Large, massive stars that are still in the main sequence can have surface temperatures as high as 50,000 kelvins. Smaller stars, such as our Sun, have surface temperatures of only a few thousand kelvins. Red giant stars, although very bright, have much cooler surfaces of about 3,600 kelvins, but they shine so strongly because they have enormous surface areas. The energy that allows stars to shine comes from nuclear fusion, the process by which light atomic nuclei, such as hydrogen, merge together to form heavier ones like helium. Each time this happens, tiny but powerful packets of energy called gamma rays are released. As this energy slowly makes its way outward through the layers of the star, it is transformed into many other kinds of electromagnetic radiation, including the visible light we can see. The colour of a star depends on the temperature of its outer layers, especially its photosphere, the thin surface from which most of its light escapes into space. Very hot stars shine with a bluish light, while cooler ones look yellow, orange, or even deep red. But stars do not only give off visible light, they emit across the entire electromagnetic spectrum, from the longest, lazy radio waves, through infrared, visible and ultraviolet, all the way to extremely short and energetic X-rays and gamma rays. Not every part of this radiation is equally powerful, but each wavelength gives astronomers valuable clues about the inner workings of the star. By carefully studying a star's spectrum, astronomers can figure out much more than just its temperature. They can measure its surface gravity, its chemical composition, sometimes called its metallicity, and even how fast it spins. If the distance to the star is known, such as by using the method of parallax, then its total luminosity, its true brightness, can be calculated. From there, astronomers can estimate its mass, radius, surface gravity, and rotation period using theoretical stellar models. In special cases, like stars that orbit each other in binary systems, their masses can be calculated directly by measuring orbital motions. There is even a technique called gravitational microlensing that has been used to weigh individual stars. Once these measurements are gathered, astronomers can also estimate the age of the star. The luminosity of a star is the total amount of light and radiant energy it produces every second. This depends strongly on its radius and surface temperature. Not all stars shine evenly across their surfaces. Vega, for example, spins so quickly that its poles are hotter and brighter than its equator. Some stars have regions on their surfaces that are cooler and therefore darker. These are known as star spots. On small stars like the Sun, they're usually small and scattered, while giant stars often have massive and easily visible star spots. These stars also show what is called limb darkening, where the edges of the star appear dimmer than the centre. Certain red dwarf stars, such as the flare star UV Ceti, may have star spots that are especially large and dramatic. The brightness of a star, as seen from Earth, is called its apparent magnitude. This depends not only on the star's luminosity, but also on how far away it is, how much its light has been dimmed by interstellar gas and dust, and how Earth's atmosphere distorts its light. Astronomers also use absolute magnitude, which is the brightness a star would appear to have if it were exactly 10 parsecs, or about 33 light-years, away from us. The system we now use to classify stars by their spectra began in the early 20th century. At first, stars were labelled with letters from A through Q based on the strength of the hydrogen absorption line in their spectra. At first, it was thought that this strength increased steadily with temperature, but later astronomers realised it was more complex. The hydrogen line actually reaches its maximum strength at around 9,000 kelvins and then weakens again at higher temperatures. The system was then rearranged into its modern form, where stars are grouped mainly by temperature. Today, stars are given a single-letter classification from O, the hottest, to M, the coolest. The sequence goes O, B, A, F, G, K, and M. Very cool. Low-mass stars and brown dwarfs are given special types such as L and T. Each letter is divided into 10 smaller steps, numbered from 0 to 9. For example, the Sun is a G2 star. However, at extremely high temperatures, the system starts to break down since stars as hot as type O0 or O1 may not even exist. Stars can also be grouped according to their size and surface gravity, which is reflected in their spectral lines. The main sequence stars, for example, are marked as class V. Giants are class of 3, hypergiants are class 0, and white dwarfs are sometimes placed in their own class, 7th. On a chart of a luminosity versus spectral type, main sequence stars form a narrow slanted band. The Sun fits neatly into this scheme as a G2V main sequence star, a yellow dwarf of average size and temperature. Extra notations are sometimes added to the spectral type to highlight special features. For example, an E means that emission lines are present, an M indicates unusually high amounts of metals, and VAR signals that the star's spectrum changes over time. White dwarfs, which are the dense remnants of dead stars, are given their own special class beginning with the letter D. These are further divided into types DA, DB, DC, DO, DZ, and DQ, depending on which spectral lines are most obvious. A number is then added to indicate the temperature. Not all stars shine steadily. Variable stars change in brightness either because of internal processes or because of external factors. Some, like pulsating variables, swell and shrink rhythmically, causing their brightness to rise and fall, with periods ranging from just a few minutes to many years. These include the famous Cepheid stars, which are crucial for measuring cosmic distances. Others, called eruptive variables, suddenly brighten because of violent flares or mass ejections. This group includes young protostars, flare stars, and massive Wolf-Rayet stars. A more dramatic group, the cataclysmic variables, undergo explosive changes. These include novae and supernovae. In certain binary systems, a white dwarf can steal gas from a nearby companion star. When enough hydrogen piles up on its surface, it suddenly fuses in a runaway reaction, causing a nova, or, if the explosion is even stronger, a type Ia supernova. Some novae repeat, with regular outbursts. Brightness changes can also be caused by outside factors. For example, in an eclipsing binary, one star passes in front of the other from our viewpoint, dimming its light. The star Algol is a famous case. Every 2.87 days, its brightness dips from magnitude 2.1 to 3.4 as one star hides the other. Inside every stable star, there is a delicate balance at work, known as hydrostatic equilibrium. Imagine taking a tiny piece of the star's interior. On that little volume, the forces pressing inward and outward almost exactly cancel each other. The inward pull comes from gravity, the star's own enormous weight pressing everything toward its center. The outward push comes from the pressure inside the star, which is stronger near the hot core and weaker toward the cooler outer layers. This difference in pressure is called a pressure gradient, and it is created by the difference in temperature between the blazing hot center and the relatively cooler surface. At the very heart of a main sequence star or a giant star, the temperature rises to at least 10 million degrees Kelvin. At such extreme heat and pressure, hydrogen atoms fuse together into helium, a process called nuclear fusion. This fusion releases vast amounts of energy, and that energy is what prevents the star from collapsing further under its own weight. When atomic nuclei fuse, they release energy in the form of extremely energetic light called gamma rays. These gamma rays do not escape the star immediately. Instead, they crash into surrounding particles of hot plasma, scattering and losing energy. Over time, this energy adds to the incredible heat in the core and slowly works its way outward. On the main sequence, stars steadily turn hydrogen into helium, very slowly increasing the amount of helium at the center. Eventually, so much helium builds up that fusion in the very core stops. For stars heavier than about 0.4 times the mass of the Sun, fusion continues in a shell around the dense helium core, which itself can no longer burn. But balance inside a star is not just about pressure and gravity. There is also thermal equilibrium, an energy balance. Energy produced in the core has to make its way outward, and the flow is steady. The amount of energy entering any layer from below exactly matches the amount leaving it above. This careful balance keeps the star stable for millions or even billions of years. The way this energy travels outward depends on the star's internal structure. In the radiation zone, energy moves mainly as light, a slow process of radiative heat transfer. Here, the plasma is calm, with no large churning motions. But if conditions change, say, if the energy flow becomes too strong, or if the material becomes too opaque to radiation, the plasma becomes unstable. Then convection begins. Giant bubbles of hot plasma rise upward, while cooler plasma sinks downward, mixing the layers like boiling water in a pot. This happens in what is called the convection zone. The locations of these zones depend on the star's size and mass. Very massive stars, several times heavier than the Sun, have convection deep inside while their outer layers are radiative. Smaller stars like our Sun are the opposite. They have radiative interiors but outer convection zones. The tiniest red dwarf stars, lighter than about 0.4 times the Sun's mass, are convective from top to bottom. Because of this complete mixing, they never build up a helium core as other stars do. As stars age, the thickness and location of these zones can shift, because the composition inside the star is slowly changing. The part of a star we actually see is called the photosphere, the thin layer where the plasma finally becomes transparent to light. From here, the energy that was born in the core millions of years earlier escapes freely into space as starlight. The photosphere is also where we see dark sunspots, cooler regions caused by magnetic activity. Above the photosphere lies the stellar atmosphere. In the Sun, the lowest part of this atmosphere is the thin chromosphere, where tall jets called spicules rise and where solar flares erupt. Higher up is the transition region, where the temperature suddenly soars within just about 100 kilometers, a tiny distance compared to the Sun's size. Beyond this lies the corona, an enormous outer layer of superheated plasma that stretches millions of kilometers into space. The corona is mysterious. Though it is hotter than the surface below, it shines very faintly because its gases are so thin. Normally we only see it during a total solar eclipse when the bright photosphere is hidden. The very existence of such a corona seems tied to the presence of convection in the star's outer layers. From the corona streams the stellar wind, a steady flow of plasma particles blowing into space. Around our Sun, this solar wind carves out a vast bubble in the galaxy known as the heliosphere, which reaches far beyond the orbit of Pluto. The power of a star comes from mass being transformed into energy. When light elements fuse, the total mass of the new nucleus is slightly less than the mass of the original particles. That missing mass is not lost. It is turned into energy according to Einstein's famous principle of mass-energy equivalence. The exact type of nuclear fusion happening in a star depends on its mass and composition. Hydrogen fusion is extremely sensitive to temperature. Even a small rise in temperature leads to a much faster reaction rate. For this reason, the cores of main sequence stars span a range, from about 4 million Kelvin in small cool red stars of class M to about 40 million Kelvin in enormous hot blue stars of class O. Our Sun, with a core of around 16 million Kelvin, fuses hydrogen into helium mainly through the proton-proton chain reaction. In stars far more massive, the story goes further. Their hot cores can ignite heavier and heavier elements. Neon, oxygen, and eventually silicon are burned in successive stages. The final product is iron-56, the most stable nucleus. But at this point the chain ends. Fusing iron does not release energy, it consumes it. When a star reaches this dead end, no more nuclear fire can hold it up, and it faces its ultimate fate through gravitational collapse. A galaxy is like a giant cosmic city, made up of stars, the leftover remains of dead stars, vast clouds of gas and dust, and an invisible substance called dark matter. All of these different parts are held together by the invisible pull of gravity. Galaxies are incredibly diverse. On average, a galaxy might hold about 100 million stars, though some are far smaller and others unimaginably larger. At the small end are dwarf galaxies, which may have fewer than 1,000 stars. At the other extreme are the supergiant galaxies, which can contain up to 100 trillion stars, all of them orbiting around the galaxy's common centre of gravity. What is perhaps most astonishing is that most of a galaxy's true mass is not in the star's gas or dust that we can see. Instead, it is hidden in the form of dark matter, which reveals itself only through its gravitational pull. At the very heart of many galaxies lurk supermassive black holes, objects so dense and powerful that not even light can escape them. Astronomers classify galaxies by their shapes, a system known as morphology. Some are smooth and rounded, called elliptical galaxies. Others are flat and graceful with swirling arms, known as spiral galaxies. Our Milky Way is one of these. A third category, the irregular galaxies, are those that don't fit neatly into either shape, often looking chaotic or distorted. The observable universe itself contains an almost unthinkable number of galaxies. Estimates range from about 200 billion to as many as 2 trillion. Most galaxies measure between 1,000 and 100,000 parsecs across, that is, about 3,000 to 300,000 light-years. The distances between them are even more staggering, often measured in millions of parsecs, which equals millions of times the distance that light can travel in a year. For example, our own Milky Way has a diameter of at least 26,800 parsecs, about 87,400 light-years. It lies a little over 750,000 parsecs, about 2.5 million light-years, from its closest large neighbour, the Andromeda Galaxy. Between galaxies, space is not completely empty. It is filled with a thin mist of gas, known as the intergalactic medium, which is so diffuse that it averages fewer than 1 atom in every cubic metre. Galaxies themselves tend to gather together into groups, clusters and superclusters. The Milky Way and Andromeda belong to the local group, which in turn is part of the much larger Virgo supercluster. At the grandest scale, even these superclusters are woven into vast sheets and filaments of galaxies, surrounding gigantic empty regions called voids. Our local group and the Virgo supercluster are themselves part of an even greater structure called Laniakea. Over the years, astronomers have catalogued millions of galaxies, but only a small number of them are known by names that are easy to remember, such as the Andromeda Galaxy, the Magellanic Clouds, the Whirlpool Galaxy, and the Sombrero Galaxy. Most others are identified only by catalogue numbers. Human beings have wondered about the Milky Way for thousands of years. The ancient Greek philosopher Democritus, who lived between about 450 and 370 years before the Common Era, suggested that the glowing band across the night sky was made of faraway stars. His contemporary Aristotle, however, thought it was caused by fiery vapours igniting in the upper atmosphere. Centuries later, the Neoplatonist philosopher Olympiodorus the Younger, who lived around the years 495 to 570 of the Common Era, argued that the Milky Way could not be atmospheric, since it did not change its appearance when seen from different places on Earth. Arab scholars carried these debates further. The brilliant scientist Ibn al-Haytham, who lived between the years 965 and 1037, was the first to attempt measuring the Milky Way's distance by checking if it showed parallax. He concluded that since it had no measurable parallax, it must be very far away and not part of Earth's atmosphere. Other thinkers such as al-Biruni, Avim Passé, and later Ibn Qayyim al-Jawziyah all offered insights, often describing the Milky Way as a vast collection of countless stars so close together that their light blended into one shining band. Real proof finally came in the year 1610, when Galileo Galilei pointed his telescope at the Milky Way and discovered that it was indeed made of a vast multitude of faint stars. In 1750, the English astronomer Thomas Wright proposed that the Milky Way might be a giant rotating system of stars held together by gravity, much like the solar system, but on a much larger scale. Only 5 years later, in 1755, the philosopher Immanuel Kant expanded on this idea, suggesting that other galaxies existed beyond our own. In 1785, William Herschel attempted the first scientific map of the Milky Way by counting stars in different regions of the sky. He thought the Sun was near the centre of a galaxy shaped somewhat like a disk. Later, in the year 1920, Jacobus Kapteyn refined the picture and imagined a small ellipsoid-shaped galaxy. Around the same time, Harlow Shapley, studying globular clusters, proposed a radically different idea. The Milky Way was a vast flat disk about 70 kiloparsecs wide, and the Sun was far from the centre. Both men were partly right and partly wrong. Their calculations did not take into account the effect of interstellar dust, which dims the light of distant stars. It was only in 1930, when Robert Julius Trumpler studied star clusters and showed how much dust affects starlight, that astronomers finally gained the modern picture of our Milky Way galaxy. On a clear and dark night, when the sky is free from city lights, a careful observer can see not just the stars of our own Milky Way, but even a few galaxies beyond it with nothing more than the naked eye. Among these visible neighbours are the Great Andromeda Galaxy, the Large Magellanic Cloud, the Small Magellanic Cloud, and the graceful Triangulum Galaxy. More than 1,000 years ago, in the 10th century, the Persian astronomer Abd al-Rahman al-Sufi made one of the earliest recorded observations of the Andromeda Galaxy. In his writings, he described it poetically as a small cloud in the heavens. Later, in the year 964, he also seems to have mentioned the Large Magellanic Cloud in his famous Book of Fixed Stars. He referred to it in terms of Al-Bakr of the Southern Arabs, though in truth, this great cloudy object lies so far to the south, at about 70 degrees below the celestial equator, that it would not have been visible from his own home. Centuries later, in the 16th century, when Ferdinand Magellan's ships ventured across the southern seas, European sailors became familiar with this mysterious glowing patch of sky. In the year 1612, the German astronomer Simon Marius also made an independent record of the Andromeda Galaxy, strengthening its place in the catalogue of the heavens. As human thought stretched wider, philosophers began to imagine what lay beyond. In the year 1734, the Swedish thinker Emanuel Swedenborg wrote in his Principia that perhaps there were other vast systems of stars far beyond our sight, organised into groups he imagined as galactic clusters. Remarkably, his early musings were strikingly similar to the way modern science now sees the universe. A little later, in the year 1745, Pierre-Louis Maupertuis suggested that some cloudy patches of light in the sky were not single objects at all, but entire gatherings of stars. He even imagined that their strange glow was greater than the light of their stars alone, and agreed with earlier ideas by Johannes Hevelius that these bright shapes might be vast spinning disks flattened by their rotation. Then, in the year 1750, Thomas Wright boldly proposed that our Milky Way itself was a giant flattened disk of countless stars, and that some of the cloudy nebulae we see may in fact be other Milky Ways, entire galaxies in their own right. By the late 18th century, efforts to record the heavens became more organised. Charles Messier created a catalogue of 109 faint cloud-like objects. Soon after, William Herschel expanded this work enormously, listing about 5,000 nebulae. In the year 1845, Lord Rosse, with his powerful telescope, looked closely at one of Messier's entries, the object now called M51, and discovered its spiral form. Today we know it as the Whirlpool Galaxy. The 20th century brought an entirely new understanding. In the year 1912, the astronomer Vesto Slipher studied the light of spiral nebulae using spectrographs. He discovered something astonishing. Many of these spirals were racing away from us at tremendous speeds, far faster than the stars within our own galaxy. This was a first hint that these nebulae were actually separate galaxies, each travelling on its own cosmic journey. In the year 1917, Heber Doost Curtis observed a nova, later called S Andromedae, inside what was then known as the Great Andromeda Nebula. By carefully examining photographs, he found 11 more novae in the same place. These new stars appeared far fainter than similar ones in our Milky Way, leading Curtis to estimate that this nebula must lie an immense distance away, about 150,000 parsecs. He became a strong supporter of the idea that these spiral nebulae were in fact island universes, independent galaxies in the vast sea of space. This bold claim led to the famous Great Debate in the year 1920 between Harlow Shapley and Curtis himself. They argued passionately about the true scale of the universe and whether spiral nebulae were part of the Milky Way or distant galaxies. Curtis pointed to features in the Andromeda Nebula, such as dark dust lanes resembling those in our own galaxy, and to the Doppler shifts Slipher had found, as evidence that Andromeda was truly another galaxy beyond ours. In the year 1922, the Estonian astronomer Ernst Öpik gave further support with his careful calculations, confirming that Andromeda lay far outside our Milky Way. A few years later, using the mighty 100-inch telescope at Mount Wilson, Edwin Hubble was able to resolve individual stars in Andromeda and other spiral nebulae. Among these stars he found Cepheid variables, which allowed him to measure their vast distances. His results proved once and for all that these nebulae were galaxies of their own, far outside the Milky Way. In the year 1926, Hubble also introduced a system of classifying galaxies by their shapes, a system that astronomers still use to this day. As time went on, each new advance in technology opened new windows to the cosmos. For centuries, astronomers had relied only on visible light, but in more recent decades they learned to study the universe across the entire spectrum of light. Dust floating in interstellar space hides much of the view in visible light, but infrared waves can pierce through, revealing the hidden hearts of star-forming clouds and the glowing centres of galaxies. Infrared light is also the key to observing galaxies so far away that their light has been stretched to redder wavelengths by the expansion of the universe. Because Earth's atmosphere blocks much of this radiation, astronomers have built telescopes on high mountains and in space itself to explore the cosmos in infrared. Soon, radio astronomy joined the quest. The Earth's atmosphere is transparent to radio waves between about 5 million cycles per second and 30 billion cycles per second, allowing scientists to detect mysterious jets streaming out from the centres of active galaxies. Even more energetic windows opened with ultraviolet and X-ray astronomy. Ultraviolet bursts have revealed distant stars being ripped apart by the powerful pull of nearby black holes, while X-rays have mapped the hot gas that fills entire clusters of galaxies. Most strikingly, X-ray astronomy has provided strong evidence that at the centre of nearly every large galaxy lies a supermassive black hole, an object millions or even billions of times heavier than our Sun. In the year 1944, a Dutch astronomer named Hendrik van der Hulst made a remarkable prediction. He suggested that a very specific kind of microwave signal, with a wavelength of 21 centimeters, should be coming from the thin clouds of hydrogen gas floating between the stars. 7 years later, in 1951, astronomers finally detected this faint signal exactly as he had predicted. This discovery was revolutionary. Unlike ordinary light, which is often blocked or scattered by the dust that fills our galaxy, this special 21 centimeter radiation passes through dust almost unhindered. Because of this, astronomers could study the motion of hydrogen gas in the Milky Way by examining the way its wavelength was stretched or compressed due to the Doppler effect. These careful observations soon revealed that the Milky Way was not just a simple spiral of stars, but that its heart contained a massive rotating bar-shaped structure. As radio telescopes improved, astronomers were able to trace the presence of hydrogen gas not only in our own galaxy, but also in countless galaxies beyond. Then, in the 1970s, an American astronomer named Vera Rubin made a discovery that shook the foundations of astrophysics. She measured how fast stars and gas clouds were moving around their galaxies and found something deeply puzzling. According to the visible matter, the stars, gas and dust, the outer regions of galaxies should have been rotating much more slowly than they actually were. Instead, galaxies were spinning far too quickly, as if some vast and invisible mass was holding them together. This mystery became known as the galaxy rotation problem, and today the best explanation is that galaxies are filled with huge amounts of a mysterious substance called dark matter, which neither emits nor absorbs light. By the 1990s, a new tool gave astronomers an even clearer view of the universe, the Hubble Space Telescope. With its sharp vision above Earth's atmosphere, Hubble confirmed that the missing mass in galaxies could not simply be explained by faint tiny stars hiding in the dark. One of Hubble's greatest achievements was the Hubble Deep Field, an image created by staring for days at a seemingly empty patch of sky. Instead of nothing, the image revealed an astonishing truth. There were around 125 billion galaxies spread across the observable universe. Even more progress came with new instruments that could see beyond the range of human eyes. Radio telescopes, infrared detectors, and X-ray observatories uncovered galaxies hidden from Hubble's view, especially in the so-called zone of avoidance, a part of the sky normally blocked by the thick stars and dust of the Milky Way. Thanks to these surveys, astronomers discovered whole new groups of galaxies that had previously been invisible. Then, in the year 2016, a team led by Christopher Consolis from the University of Nottingham published a study in the Astrophysical Journal that shocked the scientific world. By analysing a wide range of data, they concluded that the observable universe, out to a distance corresponding to a redshift of 8, contains at least 2 trillion galaxies. That is 10 times more than the number directly visible in Hubble's deepest images. Yet the story did not end there. Later, the New Horizons space probe, which had travelled far beyond the bright haze of zodiacal light that surrounds Earth, looked at the faint glow of the universe and found something unexpected. It recorded less background light than Consolis's team had predicted, suggesting that there may still be fewer galaxies than the enormous 2 trillion estimate, or perhaps that countless faint galaxies remain hidden from even our most powerful telescopes. Galaxies, the vast cities of stars in the universe, are usually grouped into 3 main types: elliptical galaxies, spiral galaxies, and irregular galaxies. Astronomers sometimes use a more detailed system, known as the Hubble sequence, to describe these galaxies based on their shapes. However, since this system focuses only on appearances, it does not always capture deeper qualities of galaxies, such as how fast they are forming new stars in starburst galaxies, or how much powerful activity is going on at the centres of active galaxies. Most galaxies, scientists now believe, hide a supermassive black hole at their heart. Even our own Milky Way galaxy has one at its centre, in a region astronomers call the Galactic Centre. Elliptical galaxies are rated in the Hubble system according to their shape, from E0, almost perfectly round, to E7, which looks stretched out like a cigar. No matter which angle you look at them from, they appear smooth, without much visible detail. These galaxies usually contain very little interstellar gas and dust. Because of this, they do not form many new stars. Instead, their light mostly comes from older, long-lived stars that orbit around the galaxy's centre in many different random directions. The stars in elliptical galaxies also contain fewer heavy elements, since most of the galaxy's star formation ended long ago after one early burst of activity. In this way, ellipticals are somewhat similar to smaller globular clusters of stars. The largest galaxies of all belong to a special category called CD galaxies, sometimes nicknamed supergiant elliptical galaxies. They were first described in the year 1964 by the astronomer Thomas A. Matthews and his colleagues. These galaxies are not only extremely large, but also the brightest and most massive galaxies ever observed. A CD galaxy typically has a dense elliptical core surrounded by an enormous faint halo of stars that can stretch across millions of light years. Compared to normal elliptical galaxies, their brightness fades away much more slowly with distance from the centre. Scientists are still studying how these cosmic giants form. The leading theory suggests that CD galaxies grow when smaller galaxies merge together inside dense galaxy clusters. Over time, these repeated mergers create a single massive galaxy, surrounded by the faint glow of leftover stars. This process can also form what astronomers call fossil groups or fossil clusters, where one huge supergiant galaxy dominates the cluster, shining from the centre and surrounded by a vast cloud of hot gas that glows in X-rays, the lingering evidence of many galactic collisions. Another idea, an older one, is called the cooling flow model. In this scenario, the hot gases inside a galaxy cluster gradually cool down and sink toward the centre, forming new stars as they collapse inward. Evidence of such cooling flows has been seen in clusters like the Perseus cluster and more recently in the Phoenix cluster. Some elliptical galaxies show an unusual feature. They appear to be wrapped in delicate concentric shells of stars, much like ripples spreading out across a pond. These are called shell galaxies, and about 1 out of every 10 elliptical galaxies shows this pattern. Astronomers think the shells form when a large galaxy swallows a smaller one. As the centres of the two galaxies move past each other and swing back, their gravitational tug creates waves of stars that pile up in shell-like layers. One striking example is the galaxy NGC 3923, which has more than 20 shells. Spiral galaxies are perhaps the most visually striking. They look like glowing pinwheels in space, with bright arms curling outward from a central bulge. While most of the visible stars and gas lie in a flat disk, the majority of their mass is hidden in a huge invisible halo of dark matter, which extends far beyond the stars. The way these galaxies rotate, known as the universal rotation curve, provides strong evidence for the presence of this mysterious dark matter. A spiral galaxy has 3 main parts: a central bulge made mostly of older stars, a rotating disk containing stars, gas, and dust, bright spiral arms that wind outward from the centre. In the Hubble system, spiral galaxies are labelled with the letter S followed by another letter, A, B, or C. These letters show how tightly wound the spiral arms are and how large the central bulge is. For example, so galaxies have tightly wound, faint arms and a big central bulge. SC galaxies have open, well-defined arms and a small central bulge. Some spiral galaxies look patchy and irregular, with fuzzy arms. These are called flocculent spirals. Others have bold, clear arms that sweep gracefully outward. These are known as grand design spirals. The flatness of a spiral galaxy's disk is connected to how fast it rotates. Some rotate slowly and appear puffed up, while others rotate quickly and are thin and sharply defined. The spiral arms themselves are not fixed structures of stars. Instead, they are density waves, regions where stars and gas get crowded together as they orbit the centre. It is similar to how cars on a busy highway may bunch up into a slow-moving wave, even though each car eventually moves past it. The arms look bright because the compressed gas in these regions gives birth to new stars, many of them hot, young, and very luminous. That is why spiral galaxies often shine with the light of fresh star formation, especially along their arms. Most spiral galaxies, including our own Milky Way, are not perfectly smooth spirals. Instead, they often have a long, straight, bar-shaped band of stars that stretches across the galaxy's core. This bar then connects smoothly to the spiral arms that wind outward. Astronomers classify these galaxies in the Hubble sequence with the letters SB, followed by a small letter A, B, or C, depending on how tightly the spiral arms are wound. Bars are not thought to be permanent features. They may form when waves of density ripple outward from a galaxy's core, or when a nearby galaxy pulls on it through gravitational tidal forces. Many barred spirals are very active because the bar channels gas toward the galaxy's centre, where it can fuel bursts of star formation or even feed a supermassive black hole. Our home galaxy, the Milky Way, is one of these barred spirals. It is shaped like a great disk with a diameter of about 30 kiloparsecs, which equals roughly 100,000 light-years. The galaxy is about 1 kiloparsec thick, or around 3,000 light-years. The Milky Way contains about 200 billion stars and has a total mass equal to about 600 billion times the mass of our Sun. Astronomers have recently identified a special kind of spiral galaxy known as superluminous spirals. These are truly enormous. Some reach across about 437,000 light-years, which makes them about 5 times wider than the Milky Way. They have masses of around 340 billion suns and shine strongly in ultraviolet and mid-infrared light. What makes them especially fascinating is their furious rate of starbirth. They form new stars about 30 times faster than the Milky Way does. Not all galaxies fit neatly into the categories of spirals or ellipticals. Some are peculiar galaxies, which have unusual shapes or properties caused by interactions with other galaxies. A striking example is the Ring Galaxy, where a ring of stars and gas circles around a nearly empty core. These rings are often created when a smaller galaxy plunges straight through the centre of a larger spiral, disturbing its stars and gas. The famous Andromeda Galaxy may have gone through such an event, as it shows multiple ring-like structures when observed in infrared light. Another intermediate type is the Lenticular Galaxy. These look like a cross between ellipticals and spirals. Classified as type S0, they have a central bulge and a disk, but only faint or poorly defined spiral arms. If they also have a bar across their centre, they are called barred lenticulars and given the classification SB0. Then there are the irregular galaxies, which, as their name suggests, have no neat or recognisable shape. Some, called Iri, show hints of structure but don't fit cleanly into the Hubble classification system. Others, called Ir2, are completely chaotic, likely because they were disturbed or torn apart by encounters with other galaxies. Close examples of irregular galaxies are the Large and Small Magellanic Clouds, which are dwarf companions of the Milky Way. Astronomers have also found dark galaxies, sometimes called ultra-diffuse galaxies. These are especially puzzling. They can be as large as the Milky Way in size, yet they contain so few stars that they shine with only about 1% of the Milky Way's brightness. Scientists believe such galaxies may have lost their star-forming gas very early, leaving behind mostly old stars. Different processes may be responsible for creating them, so there may be several types of dark galaxies. Although giant spirals and ellipticals catch the eye, most galaxies in the universe are actually dwarf galaxies. These are tiny compared to galaxies like the Milky Way, often only about 1/100th of its size and containing just a few billion stars. Some, called blue compact dwarfs, contain crowded clusters of young, hot stars that shine intensely. Others are even smaller, ultra-compact dwarf galaxies, which can be as little as 100 parsecs across. That is only about 300 light-years. Many dwarf galaxies orbit around a larger galaxy. The Milky Way itself has at least a dozen such satellite dwarfs, and astronomers estimate there could be between 300 and 500 more still waiting to be discovered. Much of what we know about dwarf galaxies comes from our local group, a small neighbourhood of galaxies that includes the Milky Way, the Andromeda Galaxy, and many dwarfs. These smaller galaxies are usually classified as irregular dwarfs or as dwarf ellipticals and dwarf spheroidals. A fascinating study of 27 dwarf galaxies close to the Milky Way revealed that no matter how many stars they contain, whether only a few thousand or millions, they all seem to have a central mass of around 10 million suns. This strongly suggests that dwarf galaxies are dominated by dark matter, the mysterious invisible material that outweighs ordinary matter in the universe. The finding also hints that there might be a lower limit to how small a galaxy can be, possibly because of the nature of dark matter itself. Some scientists even think this points to a special form of warm dark matter, which cannot clump together on very small scales. Galaxies are not isolated islands in space. They often interact with one another, and these encounters can have dramatic effects on their evolution over cosmic time. When galaxies pass close to each other without actually colliding, their immense gravitational forces tug and stretch each other, creating warped shapes and sometimes allowing a trickle of gas and dust to flow from one to the other. These near misses can leave visible distortions in their structures and subtly change their future development. Sometimes galaxies do collide, passing directly through one another. Remarkably, the stars themselves rarely crash into each other because of the vast distances between them, but the clouds of gas and dust within the galaxies do interact. These violent encounters can ignite bursts of star formation as the clouds compress and collapse under gravity. Such collisions can also dramatically reshape galaxies, forming long tails, rings, or bar-like structures that extend from their cores. At the most extreme end of these interactions are galactic mergers. Here, two galaxies approach each other too slowly to pass by, and instead they gradually combine into a single larger galaxy. Mergers can significantly transform the original shapes of the galaxies. When one galaxy is much larger than the other, astronomers call the process galactic cannibalism, because the bigger galaxy effectively swallows the smaller one, leaving the larger galaxy mostly unchanged while the smaller is torn apart. The Milky Way itself is currently in the process of cannibalizing two smaller neighbors, the Sagittarius Dwarf Elliptical galaxy and the Canis Major Dwarf galaxy. Stars are born within galaxies from reservoirs of cold gas that collect in enormous clouds known as molecular clouds. Some galaxies are capable of forming stars at an extraordinary pace, in what astronomers call a starburst. In these galaxies, the rate of star formation is so high that they would exhaust their gas supplies in a period far shorter than the galaxy's full lifespan. As a result, starburst activity is usually brief in cosmic terms, lasting only about 10 million years, a mere blink in the life of a galaxy. Starburst galaxies were much more common in the early universe, but still account for roughly 15% of all star formation in the cosmos today. Starburst galaxies are easily recognized by their dense clouds of gas and dust, and by the presence of bright, newly formed stars. Some of these stars are extremely massive and emit intense radiation, ionizing the surrounding gas to create glowing H2 regions. These stars eventually explode as supernovae, sending powerful shockwaves through the surrounding gas. These shockwaves can trigger more star formation, creating a ripple effect that spreads across the galaxy until the available gas is largely used up or dispersed. Starbursts are often linked to galaxy interactions or mergers. A famous example is the galaxy M82, which experienced a close encounter with the larger galaxy M81. Irregular galaxies, in particular, often display scattered pockets of intense star-forming activity. Some galaxies emit enormous amounts of radio waves far beyond the extent of their visible stars. These are known as radio galaxies. The giant radio-emitting regions, called lobes, are powered by energetic jets from the galaxy's central active nucleus. Radio galaxies are classified by the Fanneroff-Rayleigh system. FRE galaxies have lower radio brightness and elongated structures, while FR2 galaxies are brighter in radio and often have more pronounced lobes. This correlation between brightness and shape suggests that the processes powering these galaxies may differ. A special category is the giant radio galaxies, whose lobes can stretch across millions of light years. One of the largest known examples is Alcyonius, a low-excitation FR2 galaxy with lobes spanning 5 million parsecs, equivalent to roughly 16 million light-years. Another giant radio galaxy, 3C236, has lobes about 15 million light-years across. It's important to note that the radio lobes are not considered part of the main stellar body of the galaxy itself. Giant radio galaxies are powered by relativistic jets from a supermassive black hole at their cores, while ordinary radio galaxies can also produce radio emission from electrons accelerated by supernovae. The latter are shorter-lived, making them excellent laboratories for studying star formation. Some galaxies are labelled as active if their central region, known as an active galactic nucleus or AGN, produces a significant portion of the galaxy's total energy. Less luminous AGNs are called safer galaxies, while extremely bright ones, often outshining the rest of the galaxy, are known as quasi-stellar objects or quasars. Much of the energy from an AGN is absorbed by surrounding dust and gas, and then re-emitted at far infrared wavelengths. The standard model for an active galactic nucleus involves a supermassive black hole at the galaxy's centre, surrounded by a swirling disk of infalling matter called an accretion disk. As matter spirals inward, gravitational energy is converted into intense radiation. The AGN's brightness depends on both the mass of the central black hole and the rate at which matter falls onto it. In roughly 10% of AGNs, two energetic jets shoot out from opposite sides of the galaxy at nearly the speed of light. Despite decades of study, astronomers still do not fully understand how these jets are formed. Seyfert galaxies are among the two largest groups of what astronomers call active galaxies, the other major group being quasars. These galaxies have extremely bright energetic centers known as nuclei, which resemble those of quasars in their brightness and power. However, unlike quasars, the larger host galaxy surrounding a Seyfert nucleus can still be clearly seen. When observed through a telescope, a Seyfert galaxy often looks like an ordinary galaxy, with a particularly bright star sitting right at its core. A Astronomers classify Seyfert galaxies into two main subtypes, based on the different frequencies of light that their cores emit. Quasars, on the other hand, are some of the most powerful and distant members of the active galactic family. They shine with incredible brightness, often appearing more like stars than like extended galaxies when first discovered. This extreme luminosity, sometimes up to 100 times brighter than the Milky Way, makes them stand out across the universe. The closest known quasar, Markarian 231, lies at a distance of roughly 581 million light-years from Earth. Meanwhile, some quasars have been found at mind-boggling distances of about 13,200,000,000 light-years, such as the quasar designated UHZ-1. Quasars are also famous for demonstrating one of the universe's most fascinating phenomena, that massive objects like galaxies can bend and focus light from more distant sources, acting as a cosmic lens. Blazars are thought to be active galaxies whose energetic jets are pointed almost directly toward Earth, making their light appear especially bright. Similarly, radio galaxies produce powerful emissions at radio wavelengths through their relativistic jets. A modern unified model of active galaxies explains the differences we observe simply as the result of the angle from which we view them, rather than fundamental differences in their nature. Another intriguing category linked to active galactic nuclei and regions of intense star formation is called liners, which stands for low ionization nuclear emission line regions. The light from these galaxies is dominated by weakly ionized atoms. This faint ionization can be caused by several sources, such as aging stars in a post-asymptotic giant branch stage, active galactic nuclei or shock waves. Around 1/3 of the galaxies in our cosmic neighborhood are thought to host a liner-type nucleus. Then there are luminous infrared galaxies, or LIRGs. These galaxies emit enormous amounts of energy, with total luminosities exceeding 100 billion times that of the Sun. Most of this energy is produced by countless young hot stars heating up surrounding dust, which then re-radiates the energy as infrared light. For a galaxy to qualify as a LIRG, it must form stars at a rate of at least 18 solar masses per year. An even more extreme class, called ultraluminous infrared galaxies or ULIRGs, shines at more than 10 times the brightness of LIRGs and produces stars at over 180 solar masses per year. Many of these galaxies also host active galactic nuclei that contribute to their enormous energy output. Infrared galaxies are unique in that most of their energy emerges at infrared wavelengths, typically between 60 and 100 microns, surpassing the light emitted at all other wavelengths combined. LIRGs are often the product of violent interactions and mergers between spiral galaxies. While relatively rare in the nearby universe today, these luminous infrared galaxies were much more common when the universe was younger. Measuring the true size of a galaxy is not straightforward, because galaxies do not have sharp edges. Their star density gradually decreases as one moves outward from the center, making it difficult to define where a galaxy truly ends. Nevertheless, astronomers have developed various methods over the decades to estimate galaxy sizes. As far back as 1936, the great astronomer Edwin Hubble attempted to measure galaxy diameters. His approach relied on the apparent angle a galaxy subtended in the sky, combined with an estimated distance, resulting in what was called the angular or metric diameter. A more standardized method involves the use of the isophotl diameter. This approach defines a galaxy's size based on its surface brightness. Isophotes are lines connecting points of equal brightness in an image, and they help astronomers determine the extent of the galaxy. Brightness is measured in magnitudes per square arc second, which is a way of describing how much light is spread over a small patch of sky. For example, the center of a typical galaxy may have a brightness of 18 magnitudes per square arc second, meaning that the light is as bright as an 18th magnitude star spread evenly across that tiny area. Using this method, the isophotl diameter is usually taken to include all light down to 25 magnitudes per square arc second in the blue B band, known as the D25 standard. Another important measure of galaxy size is the half-light radius, sometimes called the effective radius, denoted as ρ. This is the distance from the center within which half of the galaxy's total light is emitted. The concept was first introduced by the French astronomer Gérard de Vaucouleurs in 1948. Although the choice of 50% was arbitrary, it proved extremely useful. In 1963, Arsène A. Fish expanded upon it, developing a law linking the brightness of elliptical galaxies to their effective radii. Then, in 1968, José Luis Cercic used a similar concept to define relationships between a galaxy's mass and its radius. To calculate the half-light radius accurately, astronomers must capture the galaxy's total brightness. One method, suggested by Burchard in the year 2000, involves measuring a radius where the local brightness flux divided by the average overall flux equals 0.2, then doubling that radius. While the half-light radius offers a rough idea of a galaxy's size, it does not tell us much about its shape or structure. Variations of this method exist. For instance, the SO Uppsala catalogue of galaxies calculates diameters using 50, 70 and 90% of the total blue light measured through a B-band filter, giving astronomers a range of ways to quantify galactic size. The concept now known as the Petrosian method was first described by the Armenian-American astronomer Vahe Petrosian in the year 1976. Since then, a refined version of this technique has been adopted by major surveys, such as the Sloan Digital Sky Survey, or SDSS. This method works by applying a mathematical model to a galaxy, where the galaxy's radius is determined by averaging its brightness in a circular or azimuthal direction. In particular, the SDSS used what is called the Petrosian magnitude in the R-band, which corresponds to a wavelength of 658 nanometers, placing it in the red part of the visible spectrum. This approach is designed to capture as much of the galaxy's light as possible, while reducing interference from background noise. For galaxies with brightness that declines exponentially from the center, the method can capture nearly all of the light. For galaxies that follow the more concentrated brightness profile described by de Vaucouleurs, it typically captures around 80% of their light. One of the key advantages of Petrosian magnitudes is that they are largely independent of a galaxy's distance or redshift, allowing astronomers to reliably measure the galaxy's apparent size. The Petrosian radius is defined based on the galaxy's total luminous flux, rather than relying on arbitrary limits. However, early versions of this method were criticized by the Infrared Processing and Analysis Center, which noted that it could produce errors in the measured brightness of up to 10% compared to using the isofocal diameter method. Another drawback is that the method can miss a significant portion of light beyond the Petrosian aperture, particularly for elliptical galaxies, although its reliability improves for galaxies at higher distances and redshifts. In response, Graham and colleagues in 2005 proposed a correction, assuming that galaxies follow the brightness profile described by Cercic's law. This approach was later adapted for use in the 2-micron all-sky survey, or 2MASS. Unlike traditional methods that use the visible light B filter, 2MASS operates in the near-infrared, which allows it to detect dimmer, cooler and older stars. Jarrett and collaborators provided a detailed description of this method, which measures multiple parameters of galaxies. In 2MASS, the standard detection area, or aperture, is defined by the infrared esophote in the K's band, which corresponds to a wavelength of about 2.2 micrometers at a brightness level of 20 magnitudes per square arc second. Astronomers use several techniques to gather the total light from a galaxy, including a circular aperture extending 7 arcseconds from the center, an isophote at 20 magnitudes per square arc second, a total aperture based on the radial distribution of light across the galaxy, and the Cron aperture, defined as 2.5 times the first moment radius of the total flux. When we look at galaxies on the grand scale, they are rarely found alone. Most galaxies exist in groups or clusters, formed and held together by mutual gravity. Truly isolated galaxies, which have avoided significant interactions with other galaxies of similar size over the last few billion years, are uncommon, making up only about 5% of surveyed galaxies. Even isolated galaxies may have merged with other galaxies long ago, or may still have smaller satellite galaxies orbiting them. On the largest cosmic scale, the universe itself is expanding, causing galaxies to drift apart over time, a relationship described by Hubble's law. Yet gravitational attraction allows galaxies within groups or clusters to resist this expansion locally. These associations of galaxies began forming early in the universe as concentrations of dark matter drew galaxies together. Smaller groups merged over time into larger clusters. This ongoing merging, along with gas falling into the cluster, heats the intergalactic gas to extreme temperatures between 30 and 100 million kelvins. Within a cluster, roughly 70 to 80% of the mass is dark matter, 10 to 30% is this superheated gas, and only a few % is in the form of the galaxies themselves. Most galaxies are gravitationally bound to multiple companions, creating a hierarchical, fractal-like structure. The smallest of these structures are known as groups, which are the most common type of galaxy cluster and contain the majority of galaxies and ordinary matter in the universe. For galaxies to remain part of a group, they must have sufficiently low velocities. If not, they may collide and merge, reducing the number of separate galaxies. Clusters are larger formations containing hundreds or even thousands of galaxies, often dominated by a single giant elliptical called the brightest cluster galaxy, which grows by tidally absorbing smaller satellite galaxies. Even larger structures, called superclusters, contain tens of thousands of galaxies organized into clusters, groups, and sometimes scattered individually. At the supercluster scale, galaxies form vast sheets and filaments that surround enormous empty regions known as voids. Beyond this scale, the universe appears mostly uniform in all directions, though recent discoveries of immense structures challenge this assumption. The largest such known structure is the Hercules Corona Borealis Great Wall, stretching an astonishing 10 billion light-years, or roughly 3 gigaparsecs. Our own Milky Way galaxy belongs to a collection known as the Local Group, a relatively small assembly of galaxies spanning roughly 1 megaparsec in diameter. The Milky Way and the Andromeda Galaxy are the two brightest members, while the rest are mostly smaller dwarf galaxies orbiting them. The Local Group itself is part of a larger cloud-like formation within the Virgo supercluster, which is centered on the Virgo cluster. This supercluster in turn is one component of an even vaster structure known as the Laniakea supercluster. Galaxies are not just vast collections of stars, gas and dust. They also possess their own magnetic fields. These invisible forces play a surprisingly important role in how galaxies behave. A galaxy's magnetic field helps shape the spiral arms, guiding the movement of gas clouds and transporting angular momentum. This movement is crucial because it allows gas clouds to collapse under their own gravity, ultimately triggering the birth of stars. In spiral galaxies, the average strength of the magnetic field is typically around 10 microgauss, which is equivalent to 1 nanotesla. To put this into perspective, the Earth's magnetic field is much stronger, averaging about 0.3 Gauss, or 30 microtesla. Some galaxies, like the Milky Way's neighbours, the Andromeda Galaxy, known as M31, and the Triangulum Galaxy, M33, have weaker fields, roughly 5 microgauss. In contrast, gas-rich galaxies that are actively forming stars such as M51, M83, and NGC 6946 have stronger fields averaging around 15 microgauss. Within the prominent spiral arms, where cold gas and dust gather, the field can reach up to 25 microgauss. The most extreme magnetic fields, reaching 50 to 100 microgauss, are found in starburst galaxies, like Métis 2 and the Antennae galaxies, as well as in nuclear starburst regions at the centers of barred galaxies such as NGC 10097. Modern models of galaxy formation are based on the LCDM, or Lambda Cold Dark Matter framework. About 300,000 years after the Big Bang, the universe underwent a momentous event known as recombination, when atoms of hydrogen and helium first formed. At this time, nearly all hydrogen was neutral, absorbing light efficiently, and no stars had yet been born. This era is often called the Dark Ages. Small variations in the density of this primordial matter eventually led to the formation of larger structures. Within cold, dark matter halos, clumps of ordinary or baryonic matter began to condense, creating the first protogalaxies, large gas clouds that were the precursors to fully formed galaxies. As gas fell into the gravitational pull of these dark matter halos, it was compressed and heated, raising its pressure and temperature. For the gas to condense further and form stars, it had to radiate away energy. This cooling process was slow because the early universe was dominated by hydrogen atoms and molecules, which are not efficient at radiating heat compared to heavier elements. Over time, as gas clumps gathered and formed rotating disks, regions within the disks reached densities high enough for star formation. The first stars to form within these protogalaxies are called Population 3 stars. These stars were made almost entirely of hydrogen and helium from the early universe. Their radiation heated nearby gas, triggering even more star formation. Ultraviolet light from these first stars reionized the surrounding neutral hydrogen in expanding bubbles, eventually affecting the entire universe, a process called reionization. The most massive of these first stars ended their lives in powerful supernova explosions, seeding the interstellar medium with heavier elements, which astronomers call metals. These metals became part of the next generation of stars known as Population 2 stars. Theoretical models of early galaxy formation have been continuously refined through sophisticated observations. Photometric observations, which measure the brightness and colours of distant galaxies, often require spectroscopic confirmation because many factors can produce misleading results. For example, a high redshift galaxy initially observed by the James Webb Space Telescope with a redshift of about 16 was later corrected to be closer to a redshift of 5. Nonetheless, confirmed observations from the JWST and other telescopes are steadily accumulating, allowing astronomers to compare early galaxies with theoretical predictions. Finding individual population 3 stars in early galaxies is even more challenging. Some initial reports have been misleading. For instance, HERT emission, once thought to indicate population 3 stars in the Cosmos redshift 7 galaxy, at a redshift of 6.60, was later found to be accompanied by oxygen emission lines inconsistent with such early stars. Once stars begin to form and emit radiation, or explode in supernovae, the process of galaxy formation becomes extremely complex. Gravity, radiation, and thermal energy interact in intricate ways, many of which remain poorly understood. Within roughly 1 billion years of a galaxy's formation, its major components start to emerge. Globular clusters form, a central supermassive black hole develops, and a bulge of metal-poor population 2 stars takes shape. The supermassive black hole plays a crucial role in regulating galaxy growth, limiting the amount of matter that can accumulate. During this early epoch, galaxies experience a major burst of star formation. Over the next 2 billion years, the accumulated matter settles into a flattened galactic disk. Throughout its life, a galaxy continues to absorb material from infalling high-velocity clouds and small dwarf galaxies, mostly composed of hydrogen and helium. The ongoing cycle of stellar birth and death gradually enriches the galaxy with heavy elements, eventually allowing planets to form. Star formation rates vary depending on a galaxy's environment. Isolated void galaxies tend to have the highest rates relative to their stellar mass, while spiral galaxies in less dense regions, called field galaxies, have moderate rates, and galaxies in dense clusters show the lowest rates. Galaxy evolution is also strongly influenced by interactions and collisions. In the early universe, mergers were common, and many galaxies had unusual, peculiar shapes. Because stars are widely spaced, most survive such encounters, but the gravitational stripping of gas and dust creates spectacular tidal tails, long streams of stars pulled from the spiral arms. Notable examples include NGC 4676 and the Antennae galaxies. Our own Milky Way galaxy is moving toward the nearby Andromeda galaxy at roughly 130 km per second. Depending on the precise details of their motions, the two galaxies may collide in about 5 to 6 billion years. While the Milky Way has never collided with a galaxy as large as Andromeda, it has merged with smaller galaxies in the past. Cosmological simulations suggest that around 11 billion years ago, the Milky Way merged with a particularly large galaxy nicknamed the Kraken. Although large-scale galaxy collisions are rare today, they were more common in the early universe. Over time, mergers between galaxies of equal size have become less frequent. Most bright galaxies have remained largely unchanged over the past few billion years, and the overall rate of star formation likely peaked about 10 billion years ago. The universe, in its vastness, is filled with countless stars, each potentially surrounded by its own family of planets. For centuries, humans could only dream of planets beyond our own solar system. We had our Earth, the Moon, Mars, Jupiter, and the other planets we could observe with our telescopes, but the notion that countless other worlds existed, orbiting distant stars far beyond our reach, seemed like the stuff of pure imagination. Yet, as science and technology progressed, these dreams slowly transformed into reality, giving rise to the fascinating and rapidly growing field of exoplanet research. Exoplanets, or extrasolar planets, are planets that orbit stars outside of our solar system. Unlike the planets in our own neighbourhood, these worlds are often difficult to detect. They do not shine with their own light like stars. Instead, they reflect the light of their parent stars or emit faint heat that is nearly impossible to distinguish from the overwhelming glow of the stars themselves. The first concrete discoveries of exoplanets came relatively recently in the grand timeline of human history. While astronomers had speculated about the existence of other worlds for centuries, it was not until the closing decades of the 20th century that observational evidence began to emerge. In 1992, the first confirmed detection of exoplanets was made, and intriguingly, it was not around a star like our Sun, but around a pulsar, a rapidly spinning remnant of a dead star. These pulsar planets were extraordinary in many ways, orbiting a stellar corpse rather than a Sun-like star, which challenged astronomers' ideas about planet formation. It was not until a few years later, in 1995, that the first exoplanet orbiting a main sequence star similar to our Sun, known as 51 Pegasi b, was discovered. This moment marked a monumental turning point in astronomy, igniting a wave of excitement and scientific inquiry that has continued to grow ever since. Detecting exoplanets is an incredible scientific challenge because these worlds are so small and faint compared to the blazing stars they orbit. Astronomers have developed several ingenious techniques to uncover their presence. One of the most successful methods is called the radial velocity method, or sometimes the Doppler method. This approach relies on observing the subtle gravitational tug that a planet exerts on its star. Even though a star is immensely more massive than its planets, a planet's gravity can cause the star to wobble ever so slightly as they orbit a common centre of mass. By measuring shifts in the star's light spectrum due to this wobble, red shifts when the star moves away from us and blue shifts when it moves toward us, scientists can infer the existence of a planet, estimate its mass, and even determine some of its orbital characteristics. Another widely used technique is the transit method, which has led to the discovery of thousands of exoplanets. This method is based on observing the slight dimming of a star's light as a planet passes directly in front of it, much like a tiny shadow crossing a distant lighthouse beam. By carefully measuring the depth and duration of this dimming, astronomers can determine the size of the planet and gain clues about its atmosphere. The advent of space telescopes, such as the pioneering Kepler Space Telescope, launched in 2009, has revolutionized the search for exoplanets. Kepler continuously monitored over 150,000 stars in a small patch of sky, detecting the periodic dips in brightness that signal transiting planets. The data collected by Kepler has been invaluable, revealing a dazzling variety of planetary systems and challenging our traditional notions of what planets can look like. Exoplanets are astonishingly diverse, both in size and composition. Some are gas giants, enormous planets composed primarily of hydrogen and helium, similar to Jupiter and Saturn in our solar system. Others are terrestrial planets, rocky worlds akin to Earth or Mars, composed of silicate rocks and metals. There are also ice giants, like Uranus and Neptune, which are dominated by icy materials such as water, ammonia, and methane. Beyond these categories, exoplanet research has revealed even stranger types of worlds. There are planets that orbit so close to their stars that their surfaces reach temperatures of thousands of degrees, called hot Jupiters, gas giants that defy our expectations by hugging their stars in blistering proximity. There are planets in highly eccentric orbits, swinging close to their star and then far away, causing extreme variations in temperature. There are even rogue planets, which drift alone through space without orbiting any star at all, wandering the galaxy as solitary travellers. The sheer variety of exoplanets has expanded our understanding of how planets can form and evolve, proving that our solar system is just one example among countless possible arrangements. Understanding exoplanets naturally leads to questions about how planets form in the first place. Planet formation is an intricate and fascinating process, intertwined with the birth and evolution of stars. Stars form from immense clouds of gas and dust, known as molecular clouds, which collapse under their own gravity. As a cloud contracts, it begins to spin, forming a flattened, rotating disk around the young protostar at its centre. This structure, known as a protoplanetary disk, is the cradle of planet formation. Within this disk, tiny dust grains collide and stick together, gradually growing from microscopic specks to larger clumps. Over thousands to millions of years, these clumps coalesce into planetesimals, objects that can range from a few kilometres to hundreds of kilometres in size. Gravity becomes increasingly important as these planetesimals grow, allowing them to attract even more material and eventually form protoplanets, the building blocks of full-fledged planets. This process, often called core accretion, is thought to be the primary pathway for forming terrestrial planets and the solid cores of gas giants. In some cases, massive regions of the disk may become gravitationally unstable and collapse directly into a planet, a process known as disk instability, which could explain the formation of some of the largest gas giants and hot Jupiters. The composition and location of planets within a protoplanetary disk are heavily influenced by temperature and the availability of materials. Closer to the young star, the disk is hotter, and volatile compounds like water and methane remain gaseous. This region favours the formation of rocky planets, composed mainly of metals and silicates. Farther from the star, temperatures drop, allowing ices to condense alongside rock, providing more material for growing planetary cores. These cores can reach sufficient mass to gravitationally attract vast envelopes of hydrogen and helium, forming gas giants. The movement of planets after formation also plays a crucial role in shaping planetary systems. Young planets can interact with the surrounding disk and with each other, causing their orbits to shift. This planetary migration can bring gas giants close to their stars or scatter smaller worlds into distant eccentric orbits. The dynamic evolution of planetary systems is a complex dance, influenced by gravity, collisions, and the shifting balance of mass throughout the system. Studying exoplanets also provides insights into the potential for habitability, the possibility that life could exist elsewhere in the universe. Scientists often focus on the habitable zone, sometimes called the Goldilocks zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. Liquid water is considered essential for life as we know it, though the discovery of extremophiles, organisms thriving in boiling hot springs, acidic lakes, and freezing Antarctic ice, suggests that life could exist in a much broader range of environments. Many exoplanets have been discovered within the habitable zones of their stars, though most of these are still far too distant for detailed study. The search for biosignatures, chemical markers of life such as oxygen, methane, or certain combinations of gases, is a central goal of future telescopes like the James Webb Space Telescope, launched in 2021. These instruments allow astronomers to analyse the atmospheres of distant worlds, looking for hints of conditions suitable for life or even evidence of biological activity. The discovery of multi-planet systems has further enriched our understanding of planet formation. Many stars host multiple planets, often arranged in orderly patterns. Some systems resemble a miniature version of our own solar system, with smaller rocky planets close to the star and larger gas giants farther away. Other systems display arrangements that are entirely unlike anything in our solar system, with massive planets orbiting very close to their stars or planets locked in complex resonances where their orbital periods are linked in precise ratios. These discoveries suggest that planet formation is a highly flexible process capable of producing a stunning variety of outcomes depending on the initial conditions of the protoplanetary disk and the interactions among forming planets. One of the most remarkable aspects of exoplanet science is the pace at which knowledge has expanded. When 51 Pegasi b was discovered in 1995, only a few planets beyond our solar system were known. Today, thousands of confirmed exoplanets have been catalogued, with many more candidates awaiting confirmation. This explosion of data has not only broadened our understanding of planetary diversity, but has also prompted the development of new theoretical models to explain the observed variety. Scientists now recognise that planets can be much more diverse than previously imagined, challenging traditional assumptions and reshaping our understanding of what constitutes a planetary system. The study of exoplanets also deepens our appreciation of the delicate conditions required for life on Earth. By comparing our solar system to the astonishingly varied planetary systems elsewhere, we see that Earth's environment is a product of countless factors aligning perfectly: the right distance from the Sun, the presence of a stabilizing moon, the protective magnetosphere, and the delicate balance of chemical elements. Observing exoplanets highlights the uniqueness of these conditions, while simultaneously suggesting that the universe may host a vast number of habitable worlds, each with its own potential for life, even if that life is radically different from what we know. In addition to the physical diversity of exoplanets, astronomers are fascinated by the potential geological and atmospheric phenomena these worlds may exhibit. Some planets may have thick, crushing atmospheres of carbon dioxide, creating extreme greenhouse effects, while others may have thin, tenuous atmospheres barely clinging to their surfaces. Some may possess vast oceans beneath icy crusts, hidden from view but teeming with chemical activity that could support life. Others may endure continuous volcanic activity, shaping the surface and releasing gases into the atmosphere. Understanding these conditions not only informs theories of planet formation and evolution, but also guides the search for planets that might host life. Observations of exoplanet atmospheres using spectroscopy reveal the presence of molecules such as water vapor, carbon dioxide, methane, and sodium, allowing scientists to infer temperature, pressure, and chemical composition, all crucial clues to the planet's history and potential habitability. Exoplanet research also intersects with the study of stellar evolution, as the life cycle of a star profoundly affects the planets around it. Young stars are often turbulent, emitting intense radiation and stellar winds that can strip away planetary atmospheres or disrupt the formation of planets entirely. As stars age and evolve into red giants or eventually into white dwarfs, their changing luminosity and size can dramatically alter the conditions on nearby planets. Some worlds may be engulfed by the expanding star, while others may experience extreme heating or cooling, reshaping their surfaces and atmospheres. These processes illustrate the deep connection between stars and their planetary companions and highlight the importance of considering the entire stellar environment when studying planet formation and evolution. Beyond individual planets and systems, the study of exoplanets informs our understanding of the galaxy as a whole. By surveying different regions of the Milky Way, astronomers can examine how planetary systems vary depending on the age, composition, and environment of their host stars. Dense star clusters, regions rich in heavy elements, and areas of intense stellar radiation each produce distinctive types of planetary systems. These observations reveal how galaxy-wide processes, such as star formation history and chemical enrichment, influence the formation and evolution of planets. By piecing together these insights, scientists begin to see not only the diversity of individual planetary systems, but also the broader patterns that govern planet formation across the galaxy. The technological advancements that have enabled these discoveries are themselves remarkable. The development of extremely sensitive detectors, precise spectrographs, space-based observatories, and sophisticated data analysis techniques has transformed the search for exoplanets from a speculative endeavour into a rigorous scientific field. Instruments such as the Transiting Exoplanets Survey satellite, launched in 2018, continue the work of Kepler by scanning nearly the entire sky for transiting planets, focusing on nearby stars that are bright enough for detailed follow-up observations. Ground-based telescopes equipped with adaptive optics, which correct for the blurring effects of Earth's atmosphere, have also contributed by directly imaging a few massive exoplanets and studying their atmospheres in unprecedented detail. Despite these achievements, many mysteries remain. Scientists are still trying to understand why certain types of planets, like hot Jupiters, are so common in other systems while absent from our own, and why some planetary systems appear incredibly orderly while others seem chaotic. The precise mechanisms that lead to the formation of terrestrial planets versus gas giants, the role of stellar metallicity, the influence of magnetic fields, and the processes that sculpt planetary atmospheres are all active areas of research. Each discovery raises new questions, driving astronomers to develop ever more sophisticated models and observational strategies. The field of exoplanet science is thus a continually unfolding story, where each new piece of data adds depth, complexity, and wonder to our understanding of the cosmos. Ultimately, the study of exoplanets and planet formation is a testament to humanity's curiosity and ingenuity. It reflects our desire to understand our place in the universe, to discover whether Earth is unique or one of countless habitable worlds, and to explore the processes that create the rich variety of planetary systems we now know to exist. From the first pulsar planets detected in 1992 to the thousands of worlds catalogued today, each exoplanet is a window into a distant solar system, a laboratory for studying the fundamental processes that shape planets, and a reminder that the universe is far more vast, complex, and intriguing than our ancestors could have imagined. As we continue to push the boundaries of observation and theory, the next decades promise even more astonishing discoveries. Planets with extreme climates, exotic compositions, hidden oceans, and perhaps even signs of life. Every new planet found is a story waiting to be told, a glimpse of the endless possibilities that the cosmos holds, and a mirror reflecting the beauty, fragility, and wonder of our own world. Exoplanets, in their staggering diversity and complexity, challenge our preconceptions, expand our imagination, and deepen our scientific understanding. The process of planet formation, though governed by the universal laws of physics, chemistry, and gravity, results in outcomes that are astonishingly varied and often surprising. From tiny rocky worlds to massive gas giants, from planets that orbit their stars serenely to those thrown into chaotic elliptical paths, the cosmos presents a panorama of planetary possibilities that continues to inspire and intrigue astronomers and dreamers alike. Every discovery adds to the mosaic, revealing not just the mechanics of planet formation, but also the profound connection between stars, planets, and the potential for life. In exploring exoplanets, humanity not only extends its knowledge of the universe but also deepens its understanding of what makes our own planet, and perhaps life itself, so remarkable. Even as our technology improves and we peer deeper into the galaxy, the exploration of exoplanets reminds us of the boundless curiosity that drives scientific inquiry. The questions are enormous. How common are Earth-like planets? Could life exist elsewhere, in forms we cannot yet imagine? How do planetary systems evolve over billions of years? Each answer leads to more questions, and each new observation offers a glimpse into the cosmic processes that shaped not only distant worlds but our own home among the stars. The field of exoplanetary science is therefore not only about finding planets, it is about understanding the story of the universe, the intricate dance of matter and energy, and the remarkable possibilities that lie beyond our tiny corner of the cosmos. As telescopes become more powerful, detection methods more precise, and theoretical models more sophisticated, the next chapters in this story promise to reveal planets even stranger, more beautiful, and more awe-inspiring than we have yet imagined, each a testament to the richness and wonder of the universe we are only beginning to explore.